This one's good. More sense because if we have to demic, remic at every speaker.
You should do that.
Yeah, but they only have one. Have two, that'd be doable. One, it's just a. You demic the other. Hey, John. Good. Yeah, so I did that earlier.
Okay, you did. I was looking, guys, like.
It's already been done. So there was the intro that was missing.
Yeah.
So I did not. I know you did, and I was like, wait, I changed it. So because I just added one thing, which is break time. There was no break. The break time was not listed. I just uploaded a new version. I put 2 zeros. Yeah,
Okay.
yeah, but whatever. I left the name that you put, so the two are there. But the other one's called. Oh, there it is.
I'll take that.
Okay, that's fine. In any case, I'm sort of, I'm gonna opening it up. No, I'll let you. let you sort of stay on the typing side. I'll handle the hooks. And if you don't listen to John, I'll throw the mic at you. Were you there in the first? Okay. 10 years, it's 10th anniversary. I actually dragged out. I found the email that Paul had sent me in 2012. He sent me this. Oh, that's that's the one that fell out. Oh, okay, the table in there.
The tables can just collapse in there. So,
That.
yeah, don't lean on that.
Okay. The remote presentation, you mean?
Yeah.
No? Okay, yeah. That worked actually in the sort of referee track. There was a presentation earlier with somebody
Yeah.
remote, and it worked for them.
Right. That's I'm just
Yeah.
hoping. Is this? I can. Yeah, that's pretty clear.
wrong, so do we. You got it wrong, then so do we. Who's Herbert? Never heard of him. Right.
Oui, ça va. Non, ça va, merci. All good. Merci. All right. Good afternoon for those of you who are in the room, and welcome if you are somewhere around the world. In that case, good evening, good afternoon, good morning, wherever it is that you are. My name is Kareem Yagmor, and on behalf of the Android Microconference Organization Committee, I'd like to welcome you to this 10th anniversary edition. Thank you, Seren, John, Jess, Amit, and Sumit who are here. So this is, the 11th time we're going to be running this. The first edition actually was prompted by an email I got from Paul McKenney in about May 2012. He said, "Hey, would you like to do a talk about Android at Plumbers?" I'm like, "What's Plumbers?" So no, I had heard about Plumbers, but I had never presented there. So that year when we ran it, we were about, I don't know, maybe 15, 20 people in the room, and we had two folks from Google. I think it was Eric Gilling and Colin Cross that had showed up that time. Over the years, we've made a tremendous amount of progress at this event. I mean, if you recall, around the Kernel Summit in 2011, there was a lot of discussion about the kernel patches for Android. I think they had gotten integrated and then thrown out, whatever. And I think a quote from LWN article states that Linus said, even if it's truly crap, we've had crap in the kernel before. So. Anyway, afterwards in December, there was a announcement by Tim Bird that there was a mainlining effort afoot for trying to get kernel patches for Android integrated. So since then, there's a lot of good progress that's been made. I think in 2014, it was Greg that came to the Android Micro Conference in Dusseldorf and asked if anybody objected to the binder driver being integrated into mainline. Obviously, sort of preaching to the choir. Android Quad was not going to say no. And if I recall correctly, it was Brian Swetland on Google Plus that responded that he'd never think he'd live to see the day for that driver to make it into mainline. So very good progress here. We have a lot of people from Google making a lot of presentations this year again, and also some of the partners they work with. So it'd be great to have participation both from people in the room and wherever you are online. All right. The format is, of course, hybrid. So this is the first time that we sort of do mainly in person and then some people remote. So we'll try to play this one by the ear. There is a single laptop, which is this one right here. You don't come with your laptop. All your slides are here, which is switch, and I'll help you out if you need help with that. The only thing we'll ask you is not to actually put any weight on the plastic thing holding the laptop because it will fall through, all right? So just, keep your hands away from the plastic thing in the middle. Right, so if you have any questions, you can ask them remotely. If you're remote, ask the questions either via chat, or you can also try to raise your hand. We'll try to get that going. If it doesn't work, please write them down in chat. They will be repeated. If you're a speaker, we'll ask you to repeat the questions. There are some mics. So Søren's taking care of the remote setup. Sumit's doing the notes. John here will give you the minutes. So please pay attention to John when he raises his laptop and shows you whatever time you have left. If you don't listen to him, I'll throw a mic at you. I'll be manning the mics myself. All right, and yeah, you got 10, 15 minutes, all right? So 15 minutes is like the hard limit. Preferably 5 minutes of talking, 10 minutes of discussion. We understand sometimes it goes a bit more. At around 10, you might find us a bit more insisting for you to start talking. There is a BOF on tomorrow that we can sort of overflow some of the stuff. It's not as long as previous BOFs. So we, you're always, free to sort of talk about stuff in the hallway and stuff. There is a 15-minute break at about 4:45 p.m. All right, it's shorter than the other breaks because, or at least supposed to be 30 minutes, but we don't have that because we want to fit in the time allocated for the MC. All right, that's pretty much it for me, I think. Yeah, we'll ask you to sort of try to do some sort of recap of what discussions have taken place regarding your specific topic. If you're a speaker, those are useful for subsequent years. It's remarkable what you can sort of gather from the stuff to see how things have moved around. All right, so my time's up. So the next presentation is about the actual GKI adoption experience. So Elliot, if you want to step forward, I will leave you the podium here.
Hello, everyone. Yeah, Kareem introduced me. I'm Elliot Berman. I'm a Qualcommer. I've been doing Android kernel integration for 2 or 3 years now. So I'm here to share how Gki has gone for Qualcomm. So last time we spoke, and I think it was 2020, we were just getting started with Gki 1.0. So I'll briefly cover what happened in Gki 1.0. I'll talk about now that we've done full Gki compliance, how that went for us, where Gki will go for us in the future, along with some out-of-tree module challenges that we've had, where we're going in the future. So yeah, back in 2020, we were doing Gki 1.0. That was just compliance testing for us. Weren't actually shipping a kernel with Gki. We were still using a diverged vendor kernel. So we've now since shifted to using a full Gki kernel in shipped devices. So that's what's new in Gki 2.0. So once we started doing that, one of the things we noticed was that we always need to be using an ACK kernel image when we're booting internally. Every time we boot a device, it should be using a Gki kernel. So we worked with Google, and we came up with this new mode of building kernels called mixed build. So we had two kernels sources sitting in our repository or in our workspace. Then we had the ACK kernel, and then we still had our traditional downstream vendor kernel called MSM kernel is usually what we call it. And we would build the Gki kernel from the ACK sources, and we build all of our vendor modules from MSM kernel. And so that let us get basically a Gki kernel booting all the time. So that was something that we learned. When we were first launching our Gki boot image, we realized that we had some embargo changes that we couldn't necessarily publish yet. Usually those changes were device identifier registers and stuff like that Qualcomm needs us to have launched device, or ARM needs us to have launched device. And so for the first few months, we weren't shipping with a converged Gki image, but now we've since converged, and you can download a public boot image for 5.10. One of the other goals of Gki was to make security patch integration much easier. We had Spectre BHP happen during 5.10. That was super easy for us to integrate, worked exactly as intended. So onto some data. So I'm trying to show how we're able to increase the number of LTS merges into our downstream tree. So they're both blue, but the one that looks worse, the greenish line, was our pre-Gki, Gki 1.0. And you can see that as you go up the graph, that's how long it took for the change to merge. And then each dot is an LTS merge. So you can see that our blue line, which is Gki 2.0, had a lot more merges, and they came in a lot more frequently. So that's kind of a net win for everyone, because part of the goal was let's get more upstream changes into the kernel. We also increased the number of contributions to upstream. So I went through the list of all the changes that we've made in the Android common kernel. We had about 125 contributions backported from kernel.org. So that's a Qualcommer upstreaming a change and then cherry picking it back on ACK. Most of the active areas were USB, UFS, and IOMU. This was the first year that we're using the upstream USB framework, and so that's why we saw a whole bunch of patches there. We had 39 contributions copied from mailing lists. That usually happens when we found some sort of bug, and it was really important for us to get it fixed quickly, so we posted the patch to the mailing list, and we just cherry picked it right away. Most of those patches end up getting accepted, but from ACK perspective, we rushed them in. Then finally, by my account, we had about 74 divergent changes, which is patches that were Android specific, excluding vendor hooks and Gki defconfig. So usually those were in memory management or scheduler changes. For instance, the asymmetric AR62 patches were mostly Android specific patches during 5.10. I believe that's mostly upstream now. So just some showing what's going on with now 13.5.15, which is this year's kernel. We have about half as many commits, so things are trending downwards across the board, which is good because it means the upstream kernel is getting a little bit higher quality for Qualcomm, which is always a good thing. So the future of Gki at Qualcomm, it went well enough for our mobile use case that we're now looking to do it outside mobile. We're exploring it, seeing if it's feasible. Some challenges there are it's not yet mandated by anyone. So we need sort of the mandate to have to do it in order to do it. We also need to optimize Gki for low memory devices. So the GKI image is a little bit large for some devices just because they have memory constraints. Some of our targets also have boot performance indicators that we have put hacks in the core kernel to help support that, and we need to upstream those. I don't know too much about them, to be honest, because they're from other non-mobile use cases, but we know that they exist. And finally, we're going to start exploring moving leaf drivers into a entirely out-of-tree project and consume ACK directly. The idea is we're going to have what am I trying to say? When we have our chip that's not yet upstream, we're going to have some drivers. And so the idea is we'll put those out of tree, let us consume LTS updates a lot faster. And some challenges we found with doing out of tree modules was kconfig. Right now, out of tree modules are kind of just left to figure out how to do target configuration, and same thing with device trees. So it'd be nice if we're working with Google to solve those issues. And then finally, output control. It'd be nice if we could have a way to just independently control the output. This isn't too much of a problem, but we're able to solve it. If you look at when you want to compile a module that's out of tree, you always have to go to the relative path. And you can't just independently control the output of a module. So it would be nice if we could independently control those, because usually we want to have the kernel output in one folder and the out of tree module folder or output in a different folder that may not be relative to the source, like from source to source. So that'd be something. So I think it was quick. So that was 5 minutes. So we can have 10 minutes of discussion. Hi, Greg.
Hey, what do you mean by, what is low memory really?
So we have, I believe, they're like IoT devices that don't have a lot of RAM. I honestly don't know. It's a lot of. I think I need to get back to you on that one because that's not directly through my team, but. Yeah, let me.
We've heard that complaint in the past, but I've never had any real numbers to show what is and what isn't.
Yeah.
And when pushed back, I found out the majority of the overhead that's caused in the GKI kernel that would prevent them from using it is from the vendors themselves.
I
Yeah.
can try to answer some part of it. One of the things was GK is only ARM64. Some of the low memory targets, they could ship ARM32. That had an impact on memory usage.
Sure, okay.
Some of it was
that's fine.
KMalek and whatnot.
Yeah.
So Caitlin was working on some patches. They'll land, that'll help quite a bit. That's the one that I'm most aware of. ARM64 brings a bunch of other changes that will increase the memory impact. So in that sense, it's true. Some of them, I think they're good impact. Like, you have some security fixes that take up more memory. Which better security is going to have some cost. But yeah, that's hopefully answers some of your question.
And there's some stuff like, I mean, KVM's compiled in, like there's features that get compiled in the GKI kernel that we just don't use. And they may not be that big of a deal on a device which has a lot of memory, but sometimes they're devices that, we really want to have as small as possible.
So
But I don't have
I agree,
specific numbers
but
for that. But like, you know
when
what I
we
mean?
ask for real numbers, what are you talking? You're talking a point of a percent of your overall memory or not? I mean, that's.
Yeah, I know. These are things that we have to get, from those use cases. But I guess the important thing is, though, just that the discussion has shifted a little bit away from why would we want to do something like GKI and use upstream kernel to we see the benefit.
That's great.
Yeah, so that's, I guess
I'm
that's
happy
kind of
to
where I
help.
want to see, like, yeah.
So to give some real numbers, ARM32 versus ARM64 with GKI, the memory impact on a particular target was about like 90 MB overhead. And that target had only 1 GB of memory. 90 MB kind of started to make a difference for them.
Well, yeah, you cannot compare ARM32 to ARM64. That's not a fair comparison.
Right, but if they're currently shipping ARM32 to do GKI, they have to do ARM64. So that's kind of how they
That's
look
an
at it.
independent thing, right?
Yeah.
You can't compare this. I can say ARM64 without GKI at a slimmed down config versus ARM64 with GKI. That's a more fair comparison.
Sorry. So you probably guessed the question, but you say, hey, we're going to move all of the drivers completely out of the kernel tree and do all of the development outside of the kernel tree. It seems like it's going to be diverging the drivers even further from upstream.
Yeah, I am a little bit worried about that too, and I'd love to hear ideas for how we can do that a little bit better. So for us, we're going to have, right now, if you look at, well, yeah, if I look at our def config for the kernel that we have, almost all of our drivers are Qualcomm specific, and they're usually all leaf drivers. And the ones that we don't have that are like pretty common, we don't make a lot of changes to those. So we're looking at seeing for like, the common storage drivers or some of those like just common framework drivers that are Qualcomm specific, if we can still use the upstream version of those and just take them from ACK. So that's a feature that Mixbuild has where we can still use driver from the actual kernel and just have the target specific part in the outer tree part and the outer tree repository. And then those get upstreamed, once the target gets launched.
Does Qualcomm upstream and then once the target gets launched, or they get released to the public and someone can upstream them if they want to?
Lennar will upstream that for us right away. That always happens within a week. So yeah, they get posted.
Nobody's asking a question. Greg, to answer your question, ARM64 versus ARM64 GKI, I think it's about 18 MB. 18 MB.
Hey, Elliot, it's Nick.
Hey, Nick. Yep.
So I found it very refreshing this past year to participate with you upstream of Android itself.
Yep.
Found that. Thank you for all the effort that you did for that.
Yeah, thanks.
Chat more with us on the K-build list about looking to do for your out-of-tree modules. And we'll figure out how to get it done.
Yeah.
And how can we encourage more participation upstream? Maybe you have some teammates or folks.
Yeah.
Anything that we can do to help with that?
Something good. I mean, from Qualcomm's perspective, we're pretty good about streaming what we can. I think a lot of our, yeah, I guess I don't really have too much specific because a lot of those drivers I think about and know about are always super target specific. And so there's not a whole lot of like change. Or there's always going to be change from year to year, but there's not a lot that's already upstream.
Cool.
You have much analysis on things like vendor hooks.
Yeah, a lot of our vendor hooks are for scheduler. And yeah. So a lot of our vendor hooks are either for scheduler or for memory dumps, RAM dump collection. I guess that's a good area for improvement that I think we maybe need to start talking about. The upstream kernel implementation for RAM dump collection is not really all that great for Qualcomm. I'd love to be able to try and move that meter a little bit more over the years, but those are mostly where our vendor hooks are. Okay.
Session is 10 minutes, so I start talking. Hi, I'm Matthias. I'm working in the Android systems team or Android kernel team in London. This is actually a talk or like a project that was inspired by the last LPC I attended in person in Lisbon, 2019, being asked what are the patches that you actually have in Android on top of an Android, on top of a Linux kernel that you need reasonably to boot. And so we started maintaining and actually a patch series for that. But first we started, what is the definition of our technical debt in this case? So we have with GKI, we developed an upstream first policy that is quite strict for every patch that we submit, especially to Android mainline or to our release branches. We require that patches are upstream, at least posted to the list, at least tracked in a way that that we have discussed whether this should actually go in the Android tree or upstream first. First, there are some difficulties about release plans, and some patches we take actually posted from list. But in general, we try to minimize the patches that we take at all. Of course, we have some patches that we need just in the Android kernel when it comes to configuration, build systems. So let's have a look. What are these patches? So as I said, it was an idea from LPC 19. We created a patch series based on just a killed patch series that we constantly rebase, basically working after Greg's merges from upstream. We try to rebase like whenever there's a new patch, we ingest it. If we have a new merge, then we rebase on top. And eventually we even pushed it out as an Android mainline tracking branch. Please don't check right now, it might be a bit outdated, but in general we can do that, and you can apply the patches on a vanilla kernel upstream, and you get the same result as Android mainline. As I said, we do serious rebases on new merges, we ingest new patches, we even fold them. We make sure that if there are some leftovers from merge conflicts or like from merge conflicts resolutions, that we clean them up, that we really have clean and neat and readable patches that are at the end on top of. We even have, like, if there's a from list patch landing upstream, it will obviously drop from the list, so we reduce our technical debt again. Then we do some classifying things that we never will upstream because they're just not relevant, like build system, like Android specific build system changes. We do metadata updates to make sure that every patch has an owner, at least known by us, that we are able to work with. And yeah, at the moment we have 224 patches. Some of them are upstream reverts that we temporarily revert, but we know exactly what we actually revert, so we can work on that. Then there are some, in the series, you will see some annotation commits, basically grouping the patches and subsystems or build system configuration changes. Then 42 changes are actually pending upstream. They are either backports from upstream that we needed earlier that will resolve at some point. Then we have from list patches that hopefully will resolve soon, but we will be able to follow up. Some of the changes that we are sent upstream are now converted to Android patches because they were not successful in its current form right now. And then there's like a bunch of patches that are only relevant for us. And most of them are in the area of where we are really local configuration changes, vendor hooks, symbol exports. Like the majority of these changes are not really upstream relevant in its current form because like nobody wants actually vendor hooks to be upstream. And symbol exports that have no user upstream will also not go upstream. Then there are some areas, a bit of a hotspot networking scheduler and some drivers, but in general it's not like crazy much. You can look up the series, there's the link here on the slides as well. But looking at them, like what happened in the last couple of years with it, we cleaned them up massively. We see like we dropped quite some lines. We upstreamed a lot of like quite some changes, like several thousand lines got upstreamed, less files get touched, and we also like Lee Jones in this case made the series very, very neat and organized. So we actually have a good view on what are the patches on top. It's not just like a bunch of random patches collected and fix-ups, and it's really a neat series. And as you can see, there are some hotspots like incremental FS or alone just takes half of our out of 3 patches in lines. You're welcome. And then there are some minor hotspots, but just 1,000 lines just go in the GKI dev config that is just not relevant upstream. So it's actually quite little, and we could maintain over the last year an average of like around 200 patches that we have. So there's tooling that we have to automate all these things, like following after, and that we just focus on the conflict resolution, and it's usually quite quick if we follow along the Android mainline, depending on how bad the merges are that come from upstream. But the less out of 3 we have, this to merge. What is it now? It's effectively an upstreaming work list, or at least we know these patches will not go upstream. We can check upstream merges that come to cross-check. Sometimes they are just like debris left over in the patches just from the merges. And we can also use these patches to cleanly revert features that we don't need anymore, or things that we just don't want anymore. For example, upstream reverts, we can make sure we actually bring the code back as without any difference to upstream. That's it. Any questions? It's more like a FYI, and how we like enforce, or like how we make sure we are reducing the out of 3 code as much as we can, and how we keep track of it. But if you have any questions about that.
As a AI effort added to the technical debt, or helped pay down technical debt?
But I think initially, when we started GKI, I think the series had like 30 patches, like in total on top. And then we accumulated a lot for the first couple of, like, I think, first year, several hundred patches, and it peaked at 800. But it was mostly about folding, organizing them. So at some point, we like came down again with GKI, and more things getting upstream, and us also bringing more things upstream to around 300, and eventually just like this, like we plateaued on this 200. So yes, GKI initially cost a bit of more out of 3, because we also had to put in the facilities for builds, hermetic tool chains, and vendor. Hi, it's me.
What?
Yeah, so this is a bit of a recent effort, but actually also as a reaction from somebody telling me your build is awful. We need to do something about it. Actually, Karim wrote me a book of an email about how hard it is to use build.sh, and how error prone it can be to get started with creating kernel modules if you're just like starting with it. So it was always overdue to do something about that, and how to rethink how we do builds for the Android kernel. But that was just a trigger, and there were reasonable and rightful complaints all over the board, and some of these things are addressed here. So what do we do actually? So if you're used to building an Android common kernel, your command line looked like using first of all, exporting an environment variable, and then calling a shell script. And in a nutshell, what we changed, we use a proper build system, or like a sophisticated build system that is not a shell script, and a proper build definition that can be tested, and that has proper dependencies, proper parallelism, and especially some other features that I'll get to. All this development is open source. While we are defining all these interfaces, none of that is happening behind closed doors. Maybe some brainstorming, but in general, every code that we do, every iteration is public, so you can like we also try to document everything along the way, so you can follow along and yeah. So building a kernel is basically Bazel build, and that definition, whoever is familiar with Bazel might recognize that common is a package and kernel arc64 is a target here. And it follows a bit of the directory structure. So where did we come from? Yeah, we came from, like, when I joined that team, I got told, here's a document, and that's how you build the kernel, and hopefully everything is in there is up to date. And if it's not, then please update it, and whoever joins next is passed on that hot potato. So, and I thought that's really not working. If you're doing things like GKI, we need stable APIs. We need to like stable APIs. We need consistent build tools across the ecosystem. We don't want to deal with environment variable bugs or anything like that. So BuildSH was yeah, published and used a lot. And now we do the next iteration with Bazel. And the implementation that we do is called Cleave. It's a bit of a wordplay with what the Android platform does with Bazel. If you want to know the details, come to me afterwards. So what BuildSH did do for us is it has some way of configuration, of configuring the build. It's not only about kernel config, but also toolchain configuration and make targets. It also does package things. It packages images. It can do module builds, external module builds. It does mixed builds, as we heard just right before. And it has a lot of control switches for like that are done with environment variables, and it was an ever-growing shell script collection, and it became difficult to maintain, especially if you have like combinations of this is a mixed build and you want to do API updates at the same time and symbolist updates, and you need untrimmed kernels and trimmed kernels, and all these things are not really like, you always have to, oh, which flag is set now, in which mode are we now? There's no consistent target definition and what are we currently doing? And as a shell script, it also has a limited parallelism as well. Hermeticity, we just like hacked in, and what you see on the right side, why is it? You see the pictures at the side, there's a bit of a screenshot. These are just like 4 screenshots of only BuildSH documentation at the beginning of the script, like documenting all the different flags and features it has. Now we switched to Bazel because the Android platform did it, and that's a reasonable choice to also eventually integrate the kernel build by source in the Android platform build. But there's more to it. Bazel is scalable, it's known to be scalable. It has proper sandboxing built in, so whatever you declare is visible to the build, whatever you don't declare is not visible to the build. So you know exactly your dependencies when it comes to toolchain, other dependencies like headers. Has quite fast incremental builds. It does a proper build analysis across, like for example, if you think of modules depending on each other. It has a better implementation of parallelism, which most build tools have these days, and integrates nicely with things like remote builds and remote caching. And how we do kernel builds is we just get environment setups that are consistent. So no matter where you run, no matter when you run, if you put the same sources in, you get the same setup. We enforce the hermetic toolchain. There's no way around to get the right compiler for the kernel. There's no way around getting the right linkers and everything in place. So if you run it on your private laptop or on another corp machine, you will get the same setup. And it all comes included. We still wrap make defconfig. We still wrap kbuild as an authoritative build system. We have plans to tweak that a bit to make it a bit more Bazel-y, but under the hood, kbuild will be the authoritative build system. So it will be still driven by kbuild. We will not write new Bazel files for core make files. The core make files stay where they are. So how does it look like? How do I define a build? The left side, you can see the actual kernel build definition comes with the default set of things like the toolchain. You don't even specify it here. You just say, here's my build config. Build config is still a thing from the build sh world that we retire. But as a way of migrating, we are using all these things, and over time, build configs will go away, and these will be flags here in these build definitions. And similarly, as you can see, there's a kernel module definition that just specifies common kernel, the one above, as a dependency. And there's no other specification of a build config. There's no specification of a tool chain. It just makes sure it inherits everything from the common kernel above. So we enforce that the module is built correctly with the right tool chain, no matter what the kernel build actually offers. And we make sure it's API compatible. And so if you build these things together, you will get a proper distribution. If you go in the subdirectory where this module lives, you can simply do bazel build NFC, the target name, and it will do everything that is needed, like possibly acquire any tool chain if it's not there for some reason, or it will make sure that the kernel is built if you need a kernel build for that. It still requires cabled makefiles, like cabled and makefile that you usually specify for modules, and we are fully compatible with that. But it limits the visibility of what you can see. For example, you only see kernel headers. You don't see source files. You see kernel tree, but it has only headers when you compile. Now, the next step that we are currently working on, that is currently in review, is a so-called driver development kit, a DDK, where you can specify, let's say, a DDK module. You put your sources in, you refer again to the common kernel, and it's simply you define drivers or modules in a way that you would, for example, in Song define a C++ library or a C library, or in Bazel a C library, by just saying these are my sources and these are the only ones that I'm seeing. These are headers. So if any module would depend on me, they would see these headers that I export. And here's the kernel build I'm depending on. And you see that, again, our NFC module, it comes with its own sources. It has nfc.h. And in case it would depend on a header file from this base module, it would just simply define it as a dependency. That would cause it to be built, obviously, afterwards. It would cause that the header file base H is visible and can be included, and only that. And lastly, it will make sure, again, the right toolchain is used. And the neat part here is all the make files, the kbuild files, and in future also the kconfig files, as much as we can, should be automatically generated under the hood. That allows us to make use of new features that come with kbuild, even though we don't need to touch the actual interface from DDK. If you were to upstream a driver that is built like that, because you're like eventually done and want to upstream it, you can literally just take that makefile that is generated and use it to upstream. There's a question.
Yes, so I see you have kernel build mentioned twice, and obviously when things are mentioned twice, the potential for. And this is only a sketch, but.
So this is a sketch. Yes, kernel build is a mandatory parameter currently. We thought of like deducting the kernel build from the other module. What we currently do is we enforce that they're consistent, so that you're using the same one. If you would use another one, but just like say, no, that's not how you do it. This answer, like this is one way forward. It's still a bit in review. We still try to figure out what is the convenient way, and obviously there will be more features that we add to it. But it's a simple way to get started. Now there's more to it. We can like one of the big complaints was like there are so many environment variables. What if they set them? Like how should I all remember that? And a Unix tool should have dash something. So the build in this case has, like, for example, bazel build dash LTO equals something, and this will apply to the entire build for the kernel and the modules. It has we have some configurations that you can consistently use, like a config fast which might be a good thing for locally, which implies thin and local compilation, where we use we break a bit out of the sandbox to use some more caching mechanisms. You can consistently enable KRSAN, and it's completely propagated across the tree. And if you would omit that flag next time, it's also made sure that all the rules are invalidated and you rebuild exactly the cases that exactly the thing that you need. Under the hood, we create a lot of like little snippets that we execute. But there are always like for example, debug print scripts will print these scripts for you and show them. Question coming in. We effectively, since Cleve is now the default system for Android 14 builds and Android mainline, we are effectively deprecating build.sh. But we also have automatic command line tools, automatic command line migrations. So for example, if you call build.sh on a branch where it's deprecated, it will actually go in, use the build system to query the exact target that you would execute instead, and will tell you exactly the command line that you have to run in the new world to use Cleve instead. Similarly, we are working on build config migration. So if you have downstream build config files yourself, we basically have a tool that says run that tool, and here's your new version of the Bazel file that you have to use instead. So we try to make migration also very easy. Yeah. One question that regularly comes up, isn't that making out-of-tree modules easier to maintain, and do we not discourage upstreaming with that? I think one answer that I regularly give is I want module development to be quite easy and approachable, and the result should be easy to also port between major versions. It should be easy to port a kernel module from, let's say, Android 13.5.15 to 14.5.15 with minimal changes, so that people that actually want to port forward towards Android mainline, towards mainline, have little work to do, or like a decreased amount of work. And by specifying exactly the dependency, what am I depending on, by forcing people to be honest about what their dependencies are, it also helps to unwind that tree of dependencies to eventually upstream one by one. Questions?
One, two. One? Okay. So yeah, so for having complained about build.sh, I just want to say that I love the solution for now. So I've not tried your solution just yet, but this is much better than build.sh that I complained about a while ago. So thank you for this.
I'm happy to hear that. Other questions? Ah, yes, sure.
Quick question. Does the Bazel handle incremental builds better than build.sh, which was not handling them at all? The incremental builds with Bazel, are they better?
So like determining what needs to be rebuilt is significantly faster. So usually like every input is tracked. So you don't have to like make usually attempts to just rebuild and early exits at certain stages, while the Bazel rules can eliminate quite quickly and invalidate quite quickly. So for example, if you just build a module, it will just if you just change the sources for a module, even though you depend on an entire kernel build, that entire kernel build will be skipped right away, because there's none of the inputs has changed, none of the input leaves or the input rules has changed. So you get right away to that kernel build. So if you think of this DDK step here, even if you build your kernel locally, like for the first time, if you touch only the kernels, the module sources, it will literally only do that. And everything else is skipped through in usually less than a second. It's like incremental builds are fast, yes. Within the rule validation. Yes, the other question.
So are there plans to use this instead of Makefile to build the actual kernel?
I don't think it's in a shape that it's suitable. I'm open to that, but I think there's like the nature of Bazel being quite heavy by itself because of all the sandboxing might be not the nicest. Or like create some effort to, or like some overhead to build up all these sandboxes and to restrict in certain tool chains, which might not be necessary upstream, and then people might be just happy with their make workflow. Also rewriting an entire build system just for the sake of it, while cabled, is actually quite nice. I don't think it's, I'm open to it, but I don't think it's necessarily the next step. Thank you.
Hello, I'm Giuliano. I also work in the Android systems team, actually for Matthias, and we're developing STG, which is an ABI tooling project as part of AOSP. So I'm going to talk a little bit about some of the ideas of STG, and really I'm looking for feedback as to whether people think they're good ideas, and also to hear what people really want from their ABI monitoring. So what's ABI monitoring? ABI monitoring, I think of it as type checking for binary objects. So we need to type check a binary object at build time against something, an ABI representation. And the ABI representation has to be produced from some other information, some ABI information source. And the sources we currently have are things like ELF, Dwarf, but there are also other things like BTF and CTF. So I'm going to show you some ABI information sources and lead into how I think we should be doing things with graphs. So this is BTF for a very small piece of software with two functions. The BTF information we get has type information, function types, and functions. And okay, so how does this look like a graph? Well, we have some nodes. I put boxes around them, so they're nodes. And obviously there's quite a lot of extra information attached to each node, like size and number of arguments, and whether a function is static linkage or not. And but we can just call those graph labels, right? So if this is a graph, those are the graph labels. And those are the edges. So in this case, we have edges for return types and edges linking functions to their types. In fact, we have two identical function types, but that's just what GCC did. Right, again, but there are also different types of edges. But we can just say if we have a different type of edge, well, that's just a different label on our edge in the graph. CTF is very similar to BTF, but what about ELF and Dwarf? So ELF has symbol information, Dwarf has type information, as well as almost everything else in the world. And we have some nodes, we have some symbols, we have some types. So on the left-hand side, we have two symbols, and on the right-hand side, we have a function declaration, the int type, and another function declaration. And the edges between them are things like this function has this type, or this symbol happens to be at this offset in this section. And that links together ELF and Dwarf. So libabigail processes ELF and Dwarf and produces an XML representation of ABIs. Is what that looks like for the same program. Again, we have a couple of nodes for symbols, a couple of nodes for function declarations, and the int type there in the middle. And there are edges expressed through XML attributes. Okay. But in all of the documentation for BTF, CTF, and libabigail, and Dwarf, the word graph is only mentioned once, and that's in the Dwarf documentation, which helpfully says that the Dwarf tree is actually a graph. Okay, so this is how I feel things are. ABI representations are graphs. We have nodes for symbols, structs, functions, all sorts of other things, and we have all sorts of different kinds of edges. Okay, but actually when we compare ABIs, we're comparing pairs of nodes and following pairs of edges. So actually we're building a comparison graph, or in the end, a diff graph. And they're you know, those things are also graphs. Different kinds of edges and nodes, but nevertheless. Why am I harping on about graphs? Well, ABI entities don't necessarily have a natural identifier. You can think of all the anonymous structs and members in the kernel, for example. Even as something as simple as a pointer, are we going to name it according to its type? That involves following edges to name things. So things don't live in a nice flat namespace. Well, symbols, I suppose, do, but most things don't. And connectivity is really important. We want to know what things depend on other things, which symbols are impacted if this type is changed, for example. And cyclic dependencies between types are really common. So the fact that this is a graph rather than a tree is quite significant. And just to recap, these are the kinds of graphs I mean. Graphs have nodes with labels and edges with labels. And we need to start somewhere when we do a comparison. So typically we start with a symbol table and compare all the symbols. And so we just need an edge to each symbol. And that's my mental model for thinking about ABI representations, even though there are multiple concrete representations out there. So this is what I hope is true. ABI representations and their comparisons are graphs. With a small number of graph algorithms and graph transformations, we can solve all or nearly all of the difficult parts of ABI monitoring. And if we can solve the problems just for sort of labeled graphs, then we can solve them for these more complex, concrete ABI representations. And we can work on the pieces independently, we can share our work, we can prove our work, we can unit test our work. This is what I hope is true. I believe at least the first part is definitely true. So, and that's because we implemented a graph comparison algorithm within STG. It uses a very simple idea of local equivalence of nodes. If you're comparing one struct type with another struct type, it does the obvious thing. And we have to follow edges in the graph in order to compare things that that struct might depend on. So it knows how to find matching edge labels and follows them and then does more work. But of course, in a graph data structure, that would be an infinite recursion. So the algorithm also knows about connectivity, knows when to stop recursing. And the end result is how we have a global equivalence of nodes, or a, if you like, a diff generation algorithm that runs in linear time on ABI graphs that can be hundreds of thousands of nodes in size. So we've kind of solved, at least with, to my satisfaction within SDG, the problem of ABI equivalence checking and diff generation. But there's plenty more to do in the ABI space, including things like ABI graph deduplication. So a lot of the really interesting things that happen within libctf and libabigail are how to take, say, raw debug information, which has massive redundancy, and compress it into a graph with no redundancy. And we haven't solved that yet within STG. But there are also other things that don't quite fit into this model of everything is an immutable graph. What if we want to only compare and I know people do this, only want to compare a subset of an ABI, say, only care about these symbols. Or perhaps we've got graphs which still contain forward declarations, but also contain definitions for certain types. We want to be able to resolve those. We also have wonderful things in the C language, like volatile const being the same as const volatile, but having two distinct representations in dwarf. And of course, type defs means we have many potentially names for the same types. And we have even more fun things like useless qualifiers on function parameters leading to distinct representations of the type for the same thing. And we need to resolve those. We'll skip the last one because it will take too long to talk about. If anyone knows what it is, they can talk to me afterwards. But graphs aren't everything. So in STG, we would ideally like a text format that gives us something suitable for version control. At the moment, we're using XML. It's okay. But really, we want a format where we have minimal ABI changes causing really minimal textual diffs, so that it's friendly to human readers, it's friendly to Garrett, it's friendly to diff and merge. When we want to talk about ABI diffs, we would like natural language descriptions of what's going on, so that people understand that a certain type in a certain place has been affected by something. So context is really important when talking about ABI breaks and changes. And at least libabigail supports the idea that maybe we want to selectively suppress certain kinds of diff. which in the graph world translates into how do you identify a node in a graph if it doesn't have a stable name? You know, how do you say, I only care about this applying to this certain thing? So maybe there's something we need to do in terms of query expressions so we can identify subsets of nodes in graphs. And there are more things we might want to do that don't sort of strictly fit in the model I was talking about. But anyway, this is how much we've done. We can load BTF into STG. We can load libabigail XML into STG. We have a comparison algorithm which runs in very predictable time. And we produce reasonably readable diff reports. But there's plenty more to do. And the next steps are to work on ELF and Dwarf and implement some of those transformations to transform graphs rather than make our comparison algorithms more complicated. So ideally, if there is only one unique representation for an ABI, that's ideal. It means we can use purely structural graph comparison to work out if ABIs are the same. And we still haven't got a format that is perfect for version control. It may not exist, but we're going to try. Any questions? Any feedback? What would you like from your ABI tooling?
Do you have any way to deal with functions that sort of hide their type? So like a function might take in a void pointer and then immediately cast it to something else?
No. I mean, that's a very hard problem. I think the only way to solve it would be with basically reconstructing the type information, which would require sort of data flow analysis within the compiler or something like that.
Just like to note an equally hideous variant of this, which I ran into in the kernel when working on the CTF DDAP machinery, which is that there are cases in which you have a single forward declaration, an opaque struct type def, with no concrete definition, and all the users cast it to something else. That I don't think you can do automatically. You'd need some sort of annotation.
Forward declarations are a significant issue, even with what we have now for the kernel. I would love to sit down with someone who has really good ideas about all the different possible ways they can cause problems. Yes. Well, thank you then. I'll repeat the question. So basically, why are we doing this when libabigail does much the same job? And that's a very good question. We can, within AOSP, target our tooling to the needs of Android, I suppose, and to be fair, to the needs of Google as a whole. I also want to take the idea of dealing with graphs, immutable graphs, as far as I can. And I think there's great value in doing that. I think by cleanly separating graphs from the transformations, from the comparisons, we'll end up with software that is easier to reason about, to maintain, and perhaps, you know, there's more space overhead than for adding complexity to do other things.
Just a quick announcement for people who join virtually. If you have a question, please click the button on the right with the hand so that we can basically give you ask a question.
Hello, everyone. Good afternoon, evening, morning, night, whatever works for you. I'm here to talk about firmware dev-link updates since the last talk I gave and some thoughts on parallelizing some of the stuff. Arrow keys don't work? There we go. Quick upstream status update. When I added firmware dev-link, it was mainly to avoid deferred probes, unnecessary deferred probes, and to implement support for sync state. But as I've been working on it, I realized it could be used to parallelize booting or suspend resume. But for that to be feasible, it means now firmware dev-link needs to be pretty thorough about all the dependencies. So I'm trying to kind of like dot the I's and T's here to make sure parallelized suspend resume or parallelized booting can work. These are the kind of changes that landed since the last LPC. I won't go into each one of them, but overall idea is debugging is a little better. Hopefully it should be easier now for people to at least report issues. Captured a few corner cases. The most important one is there's now a kernel command line to say do asynchronous boot by default for all drivers. So that's the driver async probe command line. So if you can give a star, it means default async, and then you can give a comma and like a deny list to say don't do asynchronous probing for these drivers. So by default, you can try to do as much asynchronous probing as possible. And then the other one is I change the deferred probe timeout behavior a little bit. It used to be some amount of time, but now it's changed to say try deferred probe for X amount of time after the last driver registers. So if you keep registering new drivers by adding new modules, it'll kind of keep extending the timeout because the new drivers you're adding will probably allow some probes to succeed. So that's kind of what it's trying to do. And this kind of allows me to also go and set the default timeout to 10 for config modules and firmware dev-link.strict equal to 1, which basically means treat all the dependencies as mandatory dependencies until the timeout expires. And after that, any supplier without a driver is considered an optional dependency. So you let the consumers probe, and then if they fail, they fail. If they can succeed, they can. So a bunch of work in progress or to-dos. These things haven't landed, but things I need to resolve or plan to resolve. The biggest headache for firmware dev-link is cyclic dependencies. So when I first added, I thought, okay, I'll support a simple cycle. There's not going to be anything crazier. Hindsight is 2020. When it's a simple cycle, it's like A depends on B, B depends on C, C depends on A. That was handled fine. But turns out what's right here is like a real world example of a cycle. These are the kind of cycles we need to deal with in firmware dev-link. The right way to handle this, in my opinion, is to not enforce dependencies between A, B, and C, because each of them are dependent on each other and in multiple ways. So for example, A depends on B and B depends on A, but A depends on B through 2 cycles. But we still want to enforce the ordering between X and A and Y and C. So you want to delay the probe of X until A probes, delay the probe of Y until C probes. So that's something I'm working on. There's a V1 series that I sent out a few weeks back that seems to be working. Caveat some minor bug fixes there. So I need to kind of put them in and send out a V2. I'm also thinking of, okay, once A probes first, can I assume B is the consumer of A? But then that kind of becomes tricky once you do asynchronous probing where both of them could probe at the same time. Kind of becomes hard to figure out which one really is the supplier and consumer. Maybe they're not dependent on each other at all for probing. These things will kind of start becoming important when I try to do asynchronous suspend resume. So I need to kind of figure that out there. You can look at the diagram later about the arrows and dependencies. Other improvements in progress, firmware dev-link used to depend on the DT nodes having compatible property to figure out what DT node gets converted to a struct device, and it'll try to figure out the dependencies ahead of time. Now it does a little bit more lazily so that you don't have any dependency on the existence of the compatible property. So long story short, it's a bit smarter by doing things lazily. And then it now deals with some corner case where the DT child of a DT node parent would, when it's converted to a struct device, the dependency flips, but the child is the supplier of the parent. It's there, so I have to support it. Doesn't make a lot of sense, but it's there. And the last thing I'm trying to do, it's like a pie in the sky kind of goal, which is in every framework, we have a notion of trying to say, is this like an optional supplier or not? We don't know. So we wait for a timeout, and then after that, we return an error. Until the timeout, the frameworks return eprobe differ. But it's handled like in 4 different frameworks, and they all call this function called driver deferred probe check state. Kind of trying to take it out of the frameworks so that this is all done at the core level. So the frameworks can always return an error saying enodev. But the driver code would know, okay, we haven't started allowing optional suppliers. Let's try it a few times. Nothing can probe, then we'll kind of let this probe. So I'm kind of trying to move it out so that it's cleaner on the framework levels, and then by default, all the frameworks get this support instead of them having to add one at a time. Because right now, I think it's in power domains, regulator, and IMMUs. Other long-standing to-dos for the base reason of why I added firmware link, they're still on my radar. One is to add sync state support for devices that get added to struct class. And those are kind of devices that generally don't probe. You just kind of add them, and the class manager knows what to do. Add managed device link support for class devices. Managed device links are device links that kind of order probing. Today, it allows you to add a class device as a supplier, but class device never probes. So your consumer will never probe. So this is allowed, but I need to kind of fix it so that it's handled correctly. Once that's done, I should be able to make firmware dev link be a little bit more specific about the dependency in terms of granularity. For example, if you have a PMIC that has like 10 regulators, today firmware dev link will say all the consumers are dependent on the PMIC instead of the actual regulator they depend on. So once I do the first 2, I should be able to improve the second one, the third one, so that the consumers of the regulators are actually connected to the regulators, not to the PMIC. So next, another thing to do is add sync state support for regulator framework and power domain so that the individual drivers don't need to do anything for it to work correctly. And then I've sent out a patch for clock framework, and then I kind of forgotten about it. I mean, I know about it, just haven't gotten to it. That's something I need to. And last, the one other known pain point is PHY handle DT property. PHYs are kind of force bound to their driver when an Ethernet device is open, and that kind of messes with firmware dev link because you can't really defer probe at that point. So I need to kind of figure out what to do about it there. But I think I have some ideas on that. And going to the second part of the discussion, parallelization. These are the same kind of pictures I showed last LPC, but the difference is what I'm going to talk about. Synchronous probing, asynchronous probing, mostly serialized. Asynchronous probing, the second one is basically for a static kernel. If you enable driver async probe equal to star, you can get some hundreds of milliseconds of boot savings. I want people to kind of try this and report any issues so that we can try to either make firmware dev link smarter and it captures the dependencies, or we can go mark certain devices as always synchronous, because my end goal is to enable asynchronous probing by default for at least all systems with proper firmware dev link support. And then the other thing I talked about last time was parallelized module loading. It needed some user space support. That support has now been added to Android 13. So if you set that config Android boot dot load modules parallel equal to 1, the init user space of Android 13 will load all the modules in parallel. So that gives you more boot time savings. So please give that a shot and report issues with both of these, please. And the thing that I want to discuss the most about is parallelized suspend resume, because this is the one I know the least about. My understanding of suspend resume is that it looks like drivers need to opt in, and if they opt in, they're allowed to do asynchronous suspend, and then eventually we'll kind of synchronize them based on the consumers and suppliers. So my thought is, should I add a command line that says by default do asynchronous probing for all the devices, and then because firmware dev link now has device links that ensure you don't try to suspend the supplier before the consumers finish suspending. Should it all just magically work? Hopefully, we'll see. So that's one thing. Maybe that'll only work when firmware dev link is on. That's something I could do. But then the next question is, do you really want to do asynchronous probing for every single suspend resume? Sometimes it's just faster to let the device run because it's a really small operation. So the next step is, should I start looking at keeping track of how long suspend resume takes, and say, if it's more than 250 microseconds, then do asynchronous so that it's worth context switching to another thread and letting it continue. And if we do that, then how do you let drivers to opt out of it? Those are all the kind of topics I want to talk about. Welcome any feedback. Am I going in the completely wrong direction? And that's kind of the last slide. Any questions, suggestions, thoughts? I'm surprised. I thought I'll at least get some suggestions.
I'm really worried about the class stuff. We'll have to talk offline.
Can't hear you.
I'm really worried about the class stuff. I don't think the class information should be there because class represents how the user space sees interfaces, not how the hardware is designed or interacted with at all. So it should be independent. Should be.
Okay.
I think there's probably been abuse of class in the past that is probably forcing you to do this because it is tied to hardware. Maybe we need to work on that.
Okay. Device, the only context where class matters to me is in terms of device links. But you can mark any device as a supplier. We still need to make sure you don't get blocked indefinitely if you mark a class device as a supplier.
That shouldn't be there. Class device shouldn't be a supplier.
Well, a regulator is a class device today.
Yeah, maybe that's the problem.
I think I saw, yeah, Mark Brown is right there.
I think we've gone over this before.
Okay, I
huh?
got some discussion going.
Yes, yes, it is. I didn't have a comment. You were just asking if I was here, and I'm saying I'm here.
Few minutes left. Okay, there's a question.
On the parallel suspend resume stuff, what kind of issues are you seeing? Are you seeing classes of problems that are requiring the opt-in, opt-out that you're still worried about, or what are the types of things you're seeing?
On a Pixel 6, just for the whim of it, I tried let's do all parallel suspend resume. One thing, I didn't fully analyze it to be sure about what I'm saying now, but it looked like it took longer if you try to do complete asynchronous suspend resume. That's where my question about whether I should base it on how long it takes is coming from. So if people have tried it and noticed, those are the kind of information I'd like to hear. What's the cost benefit versus asynchronous or just letting it run serially? Some suspend, I think, takes like less than a millisecond. Might not be worth waking up a new thread. And main thing, please try parallelized boot. I want to enable it by default. I don't think we're too far from it. So it's a general request to the community. Any online questions? Cool. If no questions or comments, I'm going to enable online, sorry, asynchronous suspend resume and boot. And if I break it, don't tell me that I didn't give you a chance. Thank you.
Yeah. Well, nice to meet you. Should we start early? Yeah. Okay. So hello, everyone. My name is David Brazdale. I work on the Android virtualization framework team. We also have Sherban on the video conference. So if there's any questions for our PM, answer it remotely. This slot is about how we use virtualization on Android devices. So this is different from projects like Cuttlefish that run Android in a virtualized environment. We borrow ideas from confidential computing, and we try to apply them to strengthen the application sandbox in Android. And we think that this is going to be an important piece of technology for kind of the next generation of Android use cases. So it's just going to be a very brief, high-level overview of what we've done and what are our plans. Give you some context, Android has all sorts of mechanisms for defending itself against malicious code. It starts in the application market with some malware scanning, continues on the device with the application sandbox, which is enforced with a variety of kernel features, starting with the process isolation, SE policy, C groups, etc., etc. And all this works really well, but it's a fairly large attack surface. So occasionally there's a vulnerability that leaves the devices and user data exposed until that problem is fixed. So because of that, the most crucial services in the system, stuff like Keymint, handling your crypto, or Gatekeeper, handling your authentication, those run outside of the main operating system, outside of the Linux kernel, in an isolated execution environment. It's provided by the vendors. It's typically a more privileged execution layer in the SoC. And because it's provided by vendors, it's fragmented. There's very little standardization, both in terms of APIs and the feature set. So those environments can vary quite rapidly in terms of the richness of that execution environment, how easily you can apply security updates. And there's typically no mutual distrust. So this is part of the TCB of the main operating system. If there's a vulnerability in there, it affects the rest of the system. It works fine for the current use cases, these kind of root of trust services. But because of that fragmentation, it's not something that we could expose to application developers as a development target. And it's a shame because when we look at the next crop of use cases, they're becoming more personalized, more context aware. They might be handling medical data, your digital assets, like your digital car keys these days. And they could really benefit from the assurances you get from these isolated environments. So we want to work towards building a standard implementation of that so we can scale across the ecosystem, offer that to application developers. And it also means that if we deploy more use cases into that environment, it's not going to increase the size of that TCB. So we're working towards what we call protected computing, and that environment needs to be isolated from as many components in the system as possible to reduce its attack surface. It needs to be updatable using the same containers and the same infrastructure that we use to update the rest of the system. And it needs to follow the principle of least privilege. We can't keep moving more and more code into the TCB. It needs to be a deprivileged environment. So this is where the Android virtualization framework comes in. This is where we borrow ideas from confidential computing. At the center is a hypervisor. And our reference implementation is what we call Pkvm, which is the ARM64 KVM with a new protected mode that allows you to spin up virtual machines that the host, the main operating system, cannot access. So the host remains in charge of most of the resources. It's still in charge of scheduling most devices. But the hypervisor guarantees that it cannot read or in any way access the memory of that virtual machine, and that includes DMA. So that hypervisor controls IOMMUs. Currently, the only one supported is called S2MPU. We're also working on supporting the ARM SMMU v3. It's coming soon. And the guest, this protected virtual machine, has access to new hypercalls. So it can tell the hypervisor, take some of my private memory and make it available to the host, just a subset of it. That's used for Vertio communication with bounce buffering. Another example is TRNG, so the guest needs to initialize its entropy pool somehow. So there's a hypercall to give it a bit of entropy. All of that already exists in the Android 13 common kernels, both the 5.10 and the 5.15. We're very actively working on upstreaming all of these features. If you're interested in Pkvm, we're giving a bunch of talks at KVM Forum. There's going to be a technical deep dive tomorrow morning. That might be a good talk to attend. But as I said, this is a reference implementation. So we actually allow vendors to bring their own hypervisor, and it is completely abstracted away in the architecture. Right? So the hypervisor needs to meet certain requirements, needs to expose the standard environment to the guests, but it is abstracted away for the Android app developers. So there's a Java API currently that's not public. It's not available to third-party apps. It's something we're working towards. So right now it's just platform code that can make use of this, but it can call through virtualization service, kind of like our libvirt, into CrossVM, which is our Rust-based virtual machine monitor that we share with Chrome OS, and use that to spin up either a protected or non-protected virtual machine. And we provide a kind of a base distro to run inside those VMs, which is called Microdroid. It's just a lightweight, heavily stripped down version of Android, just the Linux kernel with the very minimal user space on top that allows you to run native payloads. There's no Java in there because it would be too resource intensive. We've also extended libbinder to work over sockets. So that virtual machine can connect back to the main OS over VSOC. And they can establish a binder connection on top of it. As a result, that makes up for a very straightforward and familiar programming model to app developers. All they need to do is create a native NDK shared library, put that in their APK, and then using the API, they start a new VM. The APK gets mounted inside Microdroid, and based on some configuration, the right native library is called. That library can start a binder service on VSOC and expose that back to the Android application that's running in the main OS, right? And that can then talk to each other over binders, send commands, get results. So all of that kind of looks like talking to another process, another service in Android, but it's actually happening between two virtual machines that are mutually distrusting and fully isolated from each other. The VMs also have access to a unique secret. There was a talk on DICE this morning, so I'm not going to go into details. But basically, there's a unique device secret in every Android device, and we combine that with measurements of everything that was loaded into the VM. And through a key derivation function, we arrive at a unique secret for that particular VM instance, and it can use it to either encrypt its state between reboots, or it can derive a signing key, for example, which is what we're using in our first use case that compiles and signs system jars in this environment. All of this shipped in Android T a few months ago. There's public documentation on sourceandroid.com, and we have an email address if you want to talk to us about using some of this. And I promise this would be a very, very quick overview because I want to leave some time. Any?
Basically, this right, how it works. So the using.
Yes, so there's.
I'm not familiar with that because in my mind, the host. For some reason, in this case, it can't.
This is similar to a type 1 hypervisor like Zen, where the host is like a privileged guest. We call it type 1.5. So the APIs follow the traditional type 2 KVM model, but the guest is actually restricted from accessing the guest memory using the stage 2 MMU and IMMU. So that memory is unmapped in that stage 2 page table, and it will fault if you try to access it from the host.
Mentioned the root of trust use cases that are using kind of the vendor TEEs. Are you thinking of migrating those to this model as well?
Yeah, it's going to be a slow process, but that's what we would like to get to. Kind of right now, if you look at what get as a vendor, it's like a core package of like all the Android source code, and then a spec of all the services that you have to implement. So over time, we would like to reduce the size of that spec and just say, make sure that the hypervisor works and you get all these critical services for free. It'll be a long process, but it's something that we want to get to eventually.
Can you give some concrete use cases for virtualization in this way? What kind of thing would you expect people to be running in these VMs?
So a good example is machine learning models. Today, the use case that we already shipped is called isolated compilation. That's a platform use case where actually, you know what? We have our PM on the call. Can we give this question? Sherban, are you there?
Can you hear me?
So the question was use cases for AVF.
Yes. Can you hear me?
Yes, we can.
Okay, perfect. So I think as David mentioned, there are a number of use cases that we're working towards. They all kind of build on top of confidentiality and integrity. For example, we're looking at protecting machine learning use cases, either by protecting the IP, so the machine learning model, or protecting the data that's used to train those models. And that data could be something that's confidential or something that's personal to the user. You could think of devices becoming more intelligent and maybe using more sensors than they do today. And you can think about expanding use cases like OKG and other use cases like that. But also over time, we plan on integrating this more closely with the platform. Today, we deploy a use case called isolated compilation, where basically on OTA updates, we compile the Android framework in one of these isolated execution environments. And by doing that, we give back users a bunch of seconds or a bunch of minutes, depending on the device, that they would have otherwise waited on the first boot after an OTA update. So we think there are many use cases where we can deploy this technology. The many use cases where we use Fuzon today, and we think that it's reaching the end of the road. So overall, we're excited and hope that you folks are going to find out more about those use cases in the coming months and years. We're working internally with Google teams, but also with partners on deploying the next generation use cases for AVF.
Hey, I have a question. So I'm not sure exactly how the hardware isolation works, so that's why my question. So if you have a separate chip that is doing the trusted execution, it's a bit more isolated, right? So in this case, the virtual machine still runs on the same processor as the unprivileged stuff. So my question in the end is, do you still share the cache with like unprivileged users?
Right. So something like side channel attacks, that's that's outside of the thread model.
Okay.
So we share the same CPU. It's already done with MMU isolation. We know that there are implementations out there for trust zone that are a separate chip that try to get around what you just described, but that's not what we're trying to do.
Okay, thanks.
And time's up.
Should I start? Okay, cool. Yeah. Hey everyone, I'm Ram. I work on the Cloud Android team or Cuttlefish team over at Google and Android. Past iterations of this talk have been given by Alistair, my manager. The last one was in 2021 or 2020 with Android Automotive Virtualization. I'm just going to talk a little bit about kernel development on Cuttlefish. Let's see. So Cuttlefish is a virtual device used by kernel, BSP, and systems developers to develop for pre-silicon kernel software and various Android configurations. As for why you should use it, so we've spent the last few years becoming very VirtIO compliant from our beginning days where we had a shared memory window. So we now support a whole plethora of virtual devices, or VirtIO drivers, which enables us to support a wide variety of Kvm compliant VMMs. So we started with QEMU, and we now support CrossVM, which is a Rust-based project from Chrome OS. We also support Gem5 as of this last year, and a project from Open Synergy, which is a automotive virtualization vendor called CockOS. This then gives you, the resulting virtual device has a number of outputs, ADB, WebRTC, so you can connect to it via browser, and then serial if the device is truly borked. You can also debug the device and via GDB or printf. An interesting fun fact is that we are used to test the Upstream Linux kernel through the Android mainline tree. We do run pre-submit /CI for them across x86-64 and ARM64 when that's running again. So we do support a variety of configurations, ARM32, ARM64, x86, x86-64, across a variety of platforms, your various cloud providers, with or without GPUs, the Ampere boxes that are popping out. You can emulate us on QEMU, so that's also pretty nice. We do now support a bootloader for the past 2 years, and we also do support the boot config starting from about beginning of 2021, and we're all pretty open source, so Upstream, yeah. Some steps on how to get started developing. You just need to install a few Debian packages listed on that GitHub link over there. You can build the target off Android, and then you can build the kernel and the relevant kernel modules using the mentioned Bazel steps from the thesis presentation. Let's see. As for interacting with the device, the build will produce this wrapper called launch CVD, which just interacts with CrossVM, sets up some other processes, and then launches the device. Steps to GDB into the kernel. As for the future, we're interested in a number of use cases. We'd like to toy around with the idea of EFI booting Android. We're still talking around internally on that. EROFS, David's going to give a talk on that afterwards, but we'd also like to demo it. Running Cuttlefish on Cuttlefish just to clear out any virtualization related problems. Automotives interested in automotive VirtIO SCMI. If we were to truly be compliant, we would also toss in replay protected memory block. And then we do support GPU acceleration through VirtIO GPU, but we don't support it for ARM64 just yet. And then our camera and video encode decodes are not yet supported for acceleration. So if you would like to reach out to us with feature requests, problems, yell at us, that email, and then we have some documentation online. That sourceandroid.com link. Questions?
So if I can make a general comment, so Alistair had been suggesting I use Cuttlefish for a number of years, and sort of took me a while to sort of clue in on the value of it. And so, because I was using the emulator plenty of times. And one of the benefits that is not listed there, but at least for me is effectively I can run Cuttlefish on a cloud, not have anything connected to it, and connect to it when I want to. Whereas if I'm running the emulator, I have to hold up my desktop effectively to run the emulator. So I found that to be kind of interesting. Effectively, I can run like 20 Cuttlefishes, right, and connect to whichever one I actually want. Whereas if I'm doing work on the emulator, there's just one on my desktop. So yeah. I want to point that as one of the values of Cuttlefish is effectively that you can effectively sort of run 20 of them on a cloud and connect to whichever one that you are actually interested in.
It's interesting you mentioned that. Something we're working towards at the moment is being able to take that capacity and then launch various different Android targets, so phone, tablet, Wear device, etc., and enable them to talk over the emulated Wi-Fi and Bluetooth networks to simulate device-to-device interactions, which would hopefully improve Android interactions. But will.
You thought about running Cuttlefish in a Pkvm?
So we do have some capacity for that, though I think David might be able to flesh that out. At the moment, we can boot on non-protected mode on RockPies for the debug story that he did mention. I'm not too familiar on the Pkvm bit there, though.
Interesting if you could run it on Pixel 6 or full device.
Yeah.
In Pkvm.
We haven't tried that, right? We should.
Okay.
We actually do it the other way around. We test Pkvm with using nested virtualization.
Yes. Oh, through microdroid.
Yeah. Yeah. So right now we use nested virt on Intel to test Pkvm. So we spin up virtual machines side by side with the Cuttlefish VM, but we haven't actually tried doing it the other way around, where we would spin up Cuttlefish inside Pkvm. There have been some proposals for like, what could you use this virtualization for? Like, could we do like a compatibility story when we run an older version of Android in a VM side by side with the host? But we haven't really explored any of that.
We'll get back to you on that.
Right, so there are two questions in the chat room. So the first one is, what makes Cuttlefish better than Waydroid, or rather, what does Waydroid and Cuttlefish, how does Waydroid and Cuttlefish compare as Android targets?
What is the second target?
Waydroid.
Waydroid. Container?
I think it's a desktop thing for running Android apps. Is that right? I think we might as well skip to the other question since it's not a known target to.
I can respond to the question later.
Okay. Yeah. The second question is the Android virtualization framework also intended to allow an app to run a non-Android Linux system in a VM?
I would, if David wants to answer that one.
So technically that would be supported. Sorry. I'll take this off. Technically that is supported within AVF, but as I said, those APIs are not public yet, so it's going to need to go through review through the API Council, and we'll see where we land when the technology supports that. Sorry for stealing your Q&A around.
No.
Then thanks for having me.
So I think we got the break, right? We just do early break then? Yeah, okay. So we'll be back at the top of the hour for the continuation then. Sorry, is there one? Yeah, it's not working actually. I understand. I agree. Totally understand. No, you're right. You're totally right. Thank you for that. Sorry?
Can you come up now, or do you want stuff, or how
No,
does it work?
you can come up right now. I'll just leave you the floor. It's all yours.
Hit click, so I just click left.
Yeah, that's right.
Click right. Good to go.
Just give it a minute here. So
I'll wait till 3. I'll wait till you.
yeah, just wait a minute or two here, so people sort of, because we're like 4:58 in 4 seconds.
Oh yeah, no, don't worry. I'm not going to. I'm going to jump the gun.
No, it's just making sure everybody's back. Or,
Yeah, yeah.
you know, people are online and stuff.
Stand up for moral support until. I'm going to introduce you. I'm live, aren't I? Okay, that's cool. Mic moment.
Right, just going to ask you to start settling down because it's going to start momentarily here. So please just take a seat. Try to come up front if you can, and we'll get started with the next presentation.
Hi, I'm Paul Lawrence. I also work in the Android systems team, and this is Daniel Rosenberg. He works with me. We're working on something called Fuse BPF. That's who we are. Android has tried to use Fuse. There's some very natural use cases for Fuse in Android. One of the first was SD card FS, well, SD card before FS. The incremental file system that Matthias was staring at me while he talked about earlier was first implemented in Fuse. We've got a couple of use cases in storage. Location redaction is one that we're currently shipping, where we remove the location from images for applications that don't have location permission. And then one we're working on right now is folder hiding, where in certain areas, if you can see certain folders, you can build up a fingerprint of the device, which is a privacy violation at some level. And we want to basically hide folders that the application should be able to see by Linux rules we don't want it to see. Essentially, we want to change the file system in ways that are not that Linuxy, but that are needed for compatibility reasons or whatever. But the problem is that we have an expectation from our OEMs and actually from ourselves that we really never degrade performance. If we knock 10, 20% off performance, it's a very hard sell. In fact, there's people from, I know there's people from Qualcomm here. You'll tell us what you say to us when we remove 10% of performance. Just to stop doing it, basically. And so we have this zero. So even though Fuse is pretty good in many ways, and it's been quite highly optimized, it doesn't give us the performance we need when we try to use it in these ways. This is how we're using Fuse. We're only using Fuse currently for one of these purposes, which is location redaction, because that was a sufficiently serious security problem that we felt we had to take the performance hit. It's just a generic use of how Fuse works on with two transitions into user space. Our use cases. We had two things that came up that gave us some ideas as to how we could actually use. We still want to use Fuse. We wanted to know how, and one of the first ones was pass-through, which is the idea that you can pass through all reads and writes to a file. When you decide this file is just this file, this Fuse file should actually just be this underlying file. So we simply hook the read editor and write editor and the mapping, memory mapping, and we pass them straight through. And this solved read and write performance, as you'd expect, completely for those files. It doesn't do anything for directory operations. But the reason writes are then native performance. And then the other thing that we heard about was Xfuse, which was 3 years ago at Plumbers it was presented. It was an attempt to use BPF in Fuse to optimize. It was primarily used for optimizing attribute caching and things like that. It was a very interesting idea, but it didn't seem to go far enough. And then we've also had requests, or the people that did Fuse pass-through had requests to do directory pass-through. Now, I always felt that directory pass-through means just essentially a spine mount at that point. So, and you can't do anything. There's no control at all. You just, this directory is now this under directory. It's almost, it is a bind mount at that point to any extent. But it's useful in a small number of cases, but it's not that useful in many cases. It's just not quite flexible enough. But we felt that putting this together, putting the Fuse BPF, the Xfuse with the BPF with the pass-through would give us something that actually would solve these problems. So Daniel and myself came up with the design. It's a stacking file system. It allows any, so if there is a backing file system, I'll come to how that is set a bit later. Any request to the file system comes in. That request can be handled either by Fuse or by the backing file system. And the BPF can free up post filter these requests as needed. So that's where the flexibility comes from. Using BPF to look at the request as it comes in. You can block the request. You can change the request. You can pass it down to the underlying to the Fuse daemon for further filtering and user space if BPF doesn't give you sufficient context or whatever to make the decisions it has to make. And then it can be passed to the backing file system. And the implementation is really that we added a backing inode and a BPF program to each, or pointers to a potential backing inode and a potential BPF program to each Fuse inode structure. It can be set at mount time, or they can be set at lookup time. So when you do a Fuse lookup, I'll more on that later. We created a structure called Fuse BPF args, which if the backing inode exists, then any request if the backing inode exists in a Fuse inode, any request to that file or directory will be conditionally sent to the backing inode. If there's not one, then we're just going to behave like we're in classic Fuse mode. If no BPF, we just send it straight to the backing inode, and that's really the pass-through. That would be equivalent to the directory pass-through we talked about. If there is a BPF, then we format the Fuse BPF args. And then we send that to the BPF, so the BPF can analyze the arguments and work out what to do. And then optionally send it to a user mode filter. And it can modify the request and then send it, rather I should say. And that request is then called out to the backing file system, and then we get back the Fuse out args. And we can send those to the post filter, and then they can get the BPF post filter, which can then conditionally send it to the BPF the Fuse daemon again. I'll go through that in a couple of use cases to sort of see how that works. So this is the hiding the directories example I was talking about earlier. So we have to hook a lookup and a read dir. You don't need to do anything in the pre-filter. Once the lookup's happened, we can then analyze the return from the lookup in the post filter and simply change if the application can see the directory but should not be able to, simply change eperm to enOent as the return value, and now the lookup will no longer see the directory. It will no longer even think it's there. And then if we post filter the read dir, we can simply walk through it and remove the entries that we don't think that should not be there. Now that has to happen in user space because at this point in time, BPF, I understand it, could not do something that complicated. And then we can remove BPF from any child folders at that point. This only happens on one layer. There's one layer where we need to hide, one folder where we need to hide these folders. Below that, we just want everything to be native performance. So, and the redaction use case, which is under development, app has the media file permission, but does not have location. It can, every time you take a photograph, it can basically get your location, which is kind of a problem. We're going to replace with zeros the location in the photograph of those apps which have that combination of media permission but not location permission. So we simply need to hook the opens and store the upper limit, the high watermark of where that information could be. Then we just need to hook reads, and reads below that point will get sent to, will get post sent to user space. The user space can zero out the areas that should not be visible. So compared with a normal Fuse implementation, these are really simple solutions. It's one of the great things of implementing this. The amount of BPF you have to write is actually really small, which is very handy. The current solution to the redaction, if a file is being redacted, all reads and writes get sent to user space with obvious performance problems. They're detectable. I just wanted to show what we did with lookups. Fuse lookup, we added an extra return structure, extra optional return structure. If it's there, it allows you to keep, remove, or replace. I think we're going to change those names.
Yeah, probably.
Essentially, you can keep it, remove, or replace the backing inode and the backing BPF. So you can just point it to a different file, or you can point it at, and you can change the BPF, or you can remove it. I've only got 5 minutes, so I'm going to quickly rush through it. One really cool thing is that actually this also works on negative entries, which have been sort of going around the houses on, but it seems to give a really elegant solution to doing this on files as they're created, or as files are moved, or as links are created. With Daniel for a discussion of the verifier.
Yep. So on the verifier side, we're kind of mirroring the Fuse communication with the Fuse daemon with the Fuse arg. So we have a Fuse BPF arg, and that consists of a couple of blocks of memory of known size. And looking through the verifier, it seemed that packets were the closest fit for that. So kind of doing it more in the old BPF style. So there may be some adjustments to be done there.
Yeah, we only learned this yesterday about the old and new BPF. Thanks.
Yeah. So, question.
We have questions? Have you said what you want to say?
Oh, we'll see what the question is first.
Is this on? I don't think. Okay. So it might be tough to get a helper function, but if you guys have heard of K-funcs, K-funcs are a way of adding out to the kernel from BPF that are kind of more for targeted use cases.
All right. Yeah, that's probably what we should have been using. But
yeah. So just FYI, like I don't know if you'd have to have any verifier changes, but K-funcs that can verifier will try.
Yeah, so like the way we currently have it set up, we have kind of packets handling the verification for the edges of the buffers there. And when we want to have write access for some of these structures, for when we're dealing with strings that we're passing, we naturally can't override them, and we might need to have more space. So the helper function basically acts as the BPF requesting the ability to write into these buffers, and it converts them into allocated memory, which is either actually allocated or not.
So a use case, for example, is if you want to look up a particular file, or if the request comes in to look up a file called file, you might just want to look up a file with a slightly longer name. We clearly need to allocate something to put the longer name in to send that to the actual backing thing. That's what the function was being used for. So we need to find a way to do that in the new world.
Yeah, and it's also it's on some of the BPF presentations that there is, I guess, more of a sense of allocation now than when I was originally writing this on like a kernel version from, I don't know, several years ago.
Yeah,
Can you decide which file to map the operations to on a range by range basis? Like if you're writing to this part of the file, turn it into a write to this backing store, otherwise to that one?
So I have no, and I'm very aware of the desire to do that.
Okay.
Yeah,
I mean,
that is
so
something
we
we
really want to
intend
get
to
a
do.
version 1 up, sent
Perfectly
upstream
fine,
for
perfectly
discussion.
fine.
But I'm in the back of my mind, there are use cases where you want to have multiple trees.
Sure.
And you want to have 1 minute left. So I can really see the advantage of that. I want to chase that idea down, but I'm not quite sure how yet. See you then? Point.
Hi, can I ask a question? Do you hear me?
Yes, of course.
Hi, Paul. One quick question, if you can say whenever you will have code to show on the state of the project, at what stage it is right now, and the other question is, I was wondering about duplicating a lot of code for stacked file system, and whether you consider that you saw a lot of duplication from overlay FS, maybe something that could be factored out.
So, round of time. First, to answer your first question, we're planning to send the patches up next week.
Yeah.
And to answer your second question, I haven't considered it, and you're not the first person to bring it up.
It
But
does
we
sound
should-
like a
yes.
good idea.
But we want to get the patches up first, worry about the duplication of code second, or even third or fourth. Anyway.
Okay, and is this now production or going into production soon? What's the status?
We are going to use this in the next version of Android. That is our plan. It's solving some key problems.
Cool. Thanks.
Thanks.
All right. Floor is yours.
Hi, my name is David. I'm going to talk briefly about our experience using EuroFS in the Android ecosystem. If you're unfamiliar, EuroFS is a new read-only file system. It graduated from staging in Linux 5.4. It supports deduplication and LZ4 compression. It consistently outperforms other file systems in our real-world tests and most of our micro benchmarks. And it has one novel difference over, it's a spiritual successor to SquashFS. And the novel difference is it supports in-place decompression. This works by storing the decompressed data at the end of each page and decompressing it into the start of the same page. And in the original white paper, the strategy works on more than 99% of blocks, so it's quite effective. We've been getting tons of requests from partners about using EuroFS in Android, so we did a lot of experimentation with it and integration in Android 13. And we did a lot of our testing on Pixel. So when we tried EuroFS on Pixel, it reduced our partition sizes by about 24% on average. And with tuning, we could get this even higher. We saw up to 45% compression on our devices. And in absolute terms, that's pretty big, especially for a device with limited storage. We saw, for example, a 3.9 gig ext4 image become a 2.5 gigabyte EuroFS image. And since it supports uncompressed data and deduplication, it's on par with ext4 in terms of space requirements. So if a partner wants to use EuroFS as their file system, but not compression, that is an option. Probably the most difficult part of integrating EuroFS into Android was our OTA system. It has a pretty sophisticated block differencing scheme, which doesn't really work with compression. So what we had to do was to compare two images, decompress the LZ4 streams inside them, diff that, and then recompress them. And that strategy was super effective. We got our OTA deltas with ERFS roughly the same size as ext4. We did a few benchmarks, boot time performance on Pixel 6. ERFS uncompressed and ext4 were basically the same. And there was about a 10 to 15% boot time improvement with ERFS compression. We also did some micro benchmarks on raw read performance. This example is 4K block sizes, but we did a bunch of block size comparisons as well. And in every case, ERFS was as good as or better than ext4. One thing we did see on our app launch time benchmarks is we saw a regression with the Photos app. This benchmark simply tests how quickly the Photos app comes up on the screen. And ext4 and ERFS uncompressed were about the same, but we could see up to a 10% performance penalty with ERFS compressed. This is a whole system trace of the Photos app launch, and from here we can see what the problem is. There's just lots of CPU load, and the K-worker doing the decompression is all over the place. So we have not yet narrowed down whether scheduling latency is a big factor here versus just the time taken to do compression. But it is something to be aware of when adopting ERFS. And that's it.
Couple of questions from attendants. So the first question is, does ERFS only support LZ4 by design, or is that just a choice made here? Why not ZSTD?
So I think it does support LZMA as well right now. As to whether it could support ZSTD, I don't know. I think I read at one point that ZSTD's API was slightly different than LZ4. That might cause problems with compression, but I don't know for sure.
Question is, have you considered Btrfs? I would suspect that Btrfs plus LZ4 or ZSTD could offer similar performance while being more broadly used across the Linux ecosystem. There's also ways to do read-only and read-write separated workloads on the same volume.
Yeah, that's a great question. And we sort of raise this question amongst ourselves every year because Android goes through these cycles of deprecating and introducing file systems. Is there one file system that would just solve all of our use cases? And Btrfs comes up a lot in those discussions because it does have features like snapshotting that seem really valuable. And I think I heard yesterday that some of the Android needed features like fscrypt and fsverity were coming to Btrfs. So I think it's something we should definitely take a look at.
Just unmute yourself and ask your
Hi, can you hear me?
Yeah.
Yep.
Yeah, actually, my name is Xiang Gao. I'm not Guoren because I borrow his account. So.
Okay. Go ahead.
I'd like to answer some questions, such as ERFS is currently support LZ4, but actually we have some plan to support the STD, but I don't think that in the Android scenario it is useful to use the STD since it's cost many CPU overhead than LZ4. So that is my first answer about the STD. So the second one, I think Btrfs, actually ERFS is designed for the read-only scenario. So actually, it is not only used for system partitions, but also use container use case, since container image is also read-only. So I think that is a generic scenario more than just Android system partition or just a container image or etc. So I think it's need to optimize and design for some generic file system, more generic, more generally. So that is my answer to the ButterFS and ButterFS solution. So hope it helps.
Yeah, thank you. That's a great answer as well. That because Android system partitions are read-only, they can be highly optimized ahead of time. So it's quite likely that ButterFS isn't a great fit there, and that it might be a better fit for the data partition.
From the data side of Peter.
Oh, sorry. I wanted to respond to what you just said about ButterFS with read-only stuff, just kind of quickly. ButterFS has the ability to have subvolumes or snapshots or whatever that are read-only, and then if you wanted to, you could sprout up a read-write volume or never do that at all. So one thing that would be quite useful is like from a single ButterFS volume, your Android system data would be a read-only subvolume inside of there, and that would be a highly optimized subvolume, send, receive, stored, whatever. And the rest of the data would be on a read-write subvolume, and you would be able to eliminate like things like storage contention and have basically the storage be more flexibly allocated in that manner. So that's why I would figure that ButterFS would work pretty well for this particular case.
I just want to say about the container thing. We don't use EROFS in containers. I mean, in theory you could, but basically everyone just uses like a backing store, which maybe ButterFS or maybe something else, and then you overlay FS on top. So I mean, in theory, you could use it, but we don't use it. I'm not saying it's not useful. I'm just saying that, just commenting on that.
There's one more question. So will you be using EuroFS for Apex modules?
That's a big TBD, I think. We really want to dive into the possible issues with using K-workers for decompression first, but it's something we're looking into.
The ButterFS front, I just wanted to ask, these read-only subvolumes do depend upon DM-Verity for the entirety of those volumes. That still be possible with ButterFS, some absolute guarantee from TED. So that makes that impossible. We need a guarantee that change. DM-Verity gives us that guarantee.
So maybe I'm misunderstanding the point of these Verity things, but I would have figured FS Verity can provide similar guarantees at the subvolume layer for ButterFS.
DM-Verity as well.
Can I cut? Sorry, can I cut in some? I think that the EuroFS
Next.
Yep, looks like we lost him.
Thank you.
So John, the next person is remote, right? I'll show you all. Yes. Presenter.
Yes. Yes. Start sharing. Start sharing. Yes.
see you.
Yeah.
Flash, can you hear me?
Yeah. Hi. Should I start now?
Just 1 minute and you can go.
Okay.
Kailash, just go ahead.
Yeah. Okay. Hi everyone. My name is Kalish, and I'm on the Android systems team. Today I'll be giving a talk about our evaluation of the MGLIU patch sets in Android. So just a short background for anyone who might not be familiar. MGLIU is basically a rework of the kernel page reclaim, and basically what it does is extends on the idea of active inactive lists to multiple tiers instead of just the two. So instead of two, we have multiple generations, and this allows us to have a bit of a finer granularity control in the page reclaim. And there are also some optimizations made to the scanning. Instead of using the RMAP, we walk a list of structs, but there are some good LWN articles about this, and in the interest of time, I will not go into this further. So yeah, on Android, we care a lot about metrics like app start time and a number of low memory kills, things that affect have user visible effect. And so the test that we did is an app cycle test. We cycle about 30 apps and we perform some minimal user journeys. For instance, like we open Chrome, launch a few tabs. We open the camera app, take some photos, and then we switch to the next app. And the test is conducted in a pseudo-random order, so it's a comparable A/B testing. And we run this test for about 200 iterations. The testing device used here is the Pixel 6 Pro with 12 gigabytes RAM, and in this configuration, 3 gigabytes of ZRAM. Yeah. So yeah, we have some very interesting results, and the first metric we will look at is app launch time. So initially with the MGLIU, we didn't see the improvement in app launch time, but after we made some fixes and some workarounds to the patch set, we did see about 6.6% reduction in the overall app launch time during these tests. And also here we are comparing the ratio of hot starts. So there are three types of app start types in Android: hot, warm, and cold. And it's preferable to have hot and warm starts opposed to cold starts. So comparing the ratios of hot starts to cold starts, we see an improvement from 3.3 to about 3.8. Hot to warm is improved from about 16.8 to 19.8. And warm to cold is basically about the same. In addition to having more hot starts, we also saw that the latencies improved in the hot and warm starts. So hot starts, there was a reduction of about 3% in the average app launch latency. And for warm starts, about 3.8%. Cold starts also saw a bit of improvement, but this is probably within the margin of error. Yeah. So next metric that's important for us is the number of kills. We don't want to be too aggressive with killing apps because that obviously affects the user experience. And in here, there are three types of kills that can happen. The first is activity manager killing apps. With MGLIU, we see this actually increased about 10%. Reason why we think this happens is because MGLIU is able to keep more apps, more cached apps around, and this leads to the activity manager having to trim those cached apps because there's a threshold on the number of cached apps you can have. Yeah, so this is why there is this increase in the number of AMS kills. This LMKD kills decreased about 83%, but this number is a little bit misleading because I'll explain why. Because one of the fixes we made to the MGLIU is we use kills as a way to prevent hot-cold generation inversion, which can happen when swap is full or swap is constrained. And this is a quite common situation in Android. Android makes very utilizes the swap heavily. So this can happen a lot in Android, and the way we prevent this is by limiting the number of anonymous generations when it passes a certain threshold. In this test, when we increase the total number of generations to 8, and once the non-generations pass 6, we start doing these kills to prevent this hot-cold inversion. So that's why we see about greater than 800 kills in MGLIU and no kills in baseline. So that compensates for this drop in LMKD kills. So yeah, important to look at the overall number of kills where MGLIU does have about 8% less total kills. Yeah, there is a long-term plan for removing these kills, but I'll talk about it at the end if we have time. For working sets refaults, we see that MGLIU also has significantly better results. Anonymous pages saw a decrease in the refaults about 65%. And for file pages, we see about 81% reduction in the working set refaults, which shows that MGLIU is making much better decisions about which pages to reclaim than the baseline. The other metric we looked at is the reclaim CPU usage and efficiency. And here, this is quite significant number in terms of power management, because we saw K-swap, the CPU usage decreased by about 54% with MGLRU enabled. And also the reclaim efficiencies improved. So K-swap improved from about 32% to 57% in efficiency. Direct reclaim, there was slight regression. We'll talk about this later. This is an interesting number. And for anonymous reclaim, efficiency improved from about 16% to 40%, and file reclaim efficiency from 55 to 69%. So those are all good except for this direct reclaim. So this direct reclaim latency was an issue for the MGLIU that we found. So even though MGLIU has a lot less direct reclaims than the baseline, 81% less in these tests, it still has more stalls in the direct reclaim. Here it has about 94% increased in the stall times, in direct reclaim stall times. And looking closer at these direct reclaims, we can see why this happens exactly. So the MGLRU has a lot less direct reclaims for low latencies, low mid latencies, so less than 5 milliseconds and from 5 to 50 milliseconds. But it does have a lot more longer direct reclaims, so from 50 to 500 milliseconds and greater than 500 milliseconds. This MGLRU spends a lot of time in direct reclaim, and that's why this stall time suffers that much. Yep. So one experiment we did to try to mitigate this is increasing the swap size, because we know that MGLRU has a has a regression when the swap is constrained, which is why we have this workaround with the kills. So here in this experiment, we increased the swap size from 3 GB to 6 GB DRAM, and we do see some improvements in the launch time, about 1.5, about 1% more than with the 3 GB configuration. The direct reclaim efficiency also improved a bit, yeah, they're about the same number of direct reclaim hits, and we do see slight improvements to this stall time regression in direct reclaim. So from 94% to 52%. Yeah, so that's increasing the swap size from 3 GB to 6 GB. Yeah, one other comparison we did to between MGLRU and the baseline is with no swap device configured. So here we do see that MGLRU has does a lot better than the baseline. If you look at this number here, we see almost 50% reduction in the app launch time with no swap. And this is mostly due to the baseline is really trashing hard with no swap, because it hits MGLRU has about 99% less direct reclaim hits than the baseline in this case. So it's a lot better at preventing trashing in this type of scenario, which is not uncommon in Android for swap to be full. So yeah, it's interesting to see these results. Yeah, there are lots of other metrics that improved as well, but I won't go over them here. So here I'm trying to show is over the duration of the test, I'm showing you the number of file generations and the number of anonymous generations. So here I had increased the number of generations, total generations, to 32 in order to delay the hot cold generation inversion that can happen when the swap is full. So we see even with 32 generations during these tests, there is still this hot cold inversion, because the anonymous generations can get to this max number of generations, and when that happens, the generation counters wrap around, and this causes this type of hot cold page inversion. So this did not work. This did not help us to see better results. So what we did instead is, as I explained earlier, is we limit the number. Here we're using 8 max generations, and we limit the number. We start killing apps when the number of anonymous generations reach 6. So, and from this graph we can see that it's effective at preventing this type of hot cold inversion, because the anon generations never get to 8 or the max number of generations. Yeah, that's all the results we have to present, and now we'll take any questions or open for discussions. So yeah, well, one thing. Sorry. Yeah. So one thing I wanted to discuss is how we can improve these direct reclaim latencies. So
Before
we.
that, I do have a question. So one thing, the scenario you were generating, how realistic that is, like 30 apps cycling between them. What's the? I'm just wondering, is it that important with respect to users' experience?
Right. It's probably not that common in the real world, but we do plan to run some experiments on our fleet of devices to see what this is kind of like a edge case or worst case scenario when we have these many apps that we are switching between, so you can keep the swap full. You can keep the swap constraint for a long period of time. But yeah, in reality, it's probably not very likely. But we do plan to run some A/B experiments on our dog food devices to see what the results look like. Thank you.
All right, thank you. So we're gonna move on to the next speaker. Oh, well. Just a note for those of you who are presenting online, if you could monitor the chat, because we are going to send you the message there regarding how many minutes you got left. All right, so if you are speaking remote, just make sure you have the chat open so you can monitor John's messages about time left. Thank you. Akhilesh, you can go ahead.
So do you have the presenter rights? Okay, I have it. All right, so I'm Akhilesh from Android Systems team. Today I'm going to talk about how we use IO Uning in Android OTA. Today I'll also touch upon some of the performance results in Android OTA with IO Uning, and then the core topic, how we are trying to explore the new UBLK user space block driver. Just a quick recap to those who are not familiar with Virtual AB. Virtual AB was introduced in Android 11 for Android OTAs. Basically, it gives you seamless update, ability to roll back if the new boot fails, and it uses minimal space, wherein you don't have to duplicate dynamic partitions. The way we implement Virtual AB is through snapshots. All the dynamic partitions are implemented as snapshots. I went through this in my previous LPC. So we implement snapshots in user space in Android 13, wherein all the snapshot merging is also done in the user space. As part of the Virtual AB in Android 12 and Android 13, we introduced Android-specific curve format, wherein so we have 4 specific operations, primarily 0, wherein a block is zeroed out. Copy operation, meaning we copy the data from block X to block Y. Then we have a replace op, wherein we have to replace block X data, and that is the operation where we actually store the data in a compressed format. And then we recently introduced XOR in Android 13, where the destination block is an XOR of pre-existing block, but we just store the changed content in the curve block device. So this is the curve format we use in the Android OTA for Virtual AB. Now, given this, let's take a simple example of a snapshot merge for a copy operation. So for a snapshot merge operation, with respect to copy, we copy a data from block X to block Y, meaning we have 3 system calls here. We read the data from block X to user space, and then we write the data to block Y, and then we do an fsync. So in a typical incremental OTA, where you get a monthly security updates kind of a thing, where we have about 350 to 500K copy operations. So that results in about 1.5 million to 2 million syscalls. So what exactly are these? What is the overhead of these syscalls? So as you see here, we have the profiling data where to read the data from block X, we spend about 40% CPU cycles. And then just to write it back and then do a flush, it takes another 10 to 15%. So effectively, we are spending about 50 to 55% CPU cycles just doing the merge operation for copy operations. Now, that being said, how do we use IO here? So this is as you see, this is a very high IO bound operation. So that's where we used IO with a queue depth of 32. So with that, we were effectively cut down the CPU cycles to less than about 10 to 12%, both the read and write operations. Although we don't use SQ poll right now, but if we are trying to explore that as well. But with SQ poll enabled, we can effectively cut down all the syscalls completely. So what exactly does this mean, cutting down CPU cycles with respect to snapshot merge? So all this means we are cutting down the snapshot merge time. So for instance, on Pixel 6, running the latest Android T, with IO enabled, we were able to see merge time completion in about 60 to 75 seconds for an incremental OD of about 200 MB. Without IO it used to take about 2 to 3 minutes. In a worst case, for instance, we have seen instances where it goes all the way up to 10 to 20 minutes as well. Now, why do we need snapshot merge to be completed fast? Because that is the next slide. So until the snapshot merge is completed, all the slash system, the root file system is mounted off DM user. So DM user is a kernel module, just like it's a user space block, emulating the user space block device. So it's an out-of-tree kernel patch today where we maintain specific for Android devices on 5 different kernels. So until snapshot merge is completed, all the IO from slash system or slash product goes to DM user, and DM user routes that IO to the user space. And we have a user space daemon called snap user D, which actually handles the IO activity. So there are 2 drawbacks here. One, we have to maintain. It's a technical debt of maintaining the DM user on different kernels as we go down the path. Second, from the profiling, we see that there is an overhead of about 10% CPU, meaning that anytime you do any IO activity until merge is completed, for instance, you launch an app, and the app launch IO has to go to DM user. So there is constant back and forth operation between user space and kernel. So that is an overhead. So to address this problem, we are exploring the new UBLK driver, which just got merged upstream in 520. So this is an UBLK is a user space block driver, which is IO based, meaning all the IO. So we have the UBLK driver and you have the UBLK server. The communication between this server and the UBLK driver happens through the newly added IO op command. So with this, it perfectly fits the existing architecture of what we were looking into. We're still in the exploration phase, but we had a bare minimal prototype completed on Pixel 6 running Android mainline and with an UBLK driver target enabled on 6.0 RC1 build. The only difference we have with the current architecture is that we have to stack DM linear on top of UBLK driver. So I'll come to that in the next slide, why we do that. But the primary changes we are looking at right now here is that we'll be adding a new UBLK Android target, which will communicate with the daemon, meaning that any IO request we get from the UBLK block driver, that IO request will be handled by the new target. So currently, the daemon, UBLK server daemon handles only the loopback target, which we need it for copy operations. But we also need it for other Android-specific operations like replace, XOR, and zero op. So that will be handled by the UBLK Android target. With the bare minimal prototype completed on Pixel 6, we saw some really promising numbers, wherein we could essentially see some of the latency cut down with the new driver. Now, that being said, So there are some couple of challenges here. One, why do we need to stack DM linear on top of UBLK driver? There are two issues here. One, once the snapshot merge is completed, we need to remove the UBLK block driver so that /system is mounted off the underlying base device. So the life cycle of the block driver, UBLK block driver, should only be until the snapshot merge is done. Now, the device mapper infrastructure gives us the ability to switch DM tables once the merge is completed, meaning we can suspend the IOs and then resume the IOs. That infrastructure is not present today in UBLK block driver. That is something which we probably will have to enhance it, or we're trying to see how effectively we can do it, because we don't know the overhead of stacking DM linear on top of UBLK driver. So that is one. Second, during the Android boot phase, so between Android first stage and second stage daemon, we have an intermediate stage called SALinux transition, wherein we set the labels to the user space processes. So as you see here, the file system is mounted on top of UBLK driver. So this happens right at the first stage init. So during first stage init, there are no SALinux context. So all the IO activities will still be served by the daemon. But when we have to set the labels to the daemon, we have to kill the daemon and restart the daemon. So there's a small duration in time where the IOs have to be paused or queued in the driver, because there's a duration where we have to relaunch the daemon with the right set of SALinux labels, which means that some amount of queuing is required in the UBLK block driver. So those are the two primary challenges which we are looking at right now. We are still prototyping this work. Hopefully, we should have this in the upcoming Android releases. And there are, of course, some trivial changes in the server as well, since we see that UBLK server uses some of the C++20 operations like coroutines, which are not supported in Android. So we may have to change some of those. But yeah, with this, the result is that we don't have any out of tree kernel patch. That is a big plus point. And second, everything related to the OTA is in user space. So we have effectively in control for the specific Android core format devices. With that, I will open the floor for the questions. So let's see if we have any questions in the chat room.
It seems like IOUing is kind of exploding within the kernel ecosystem, and people are rushing to add lots of new use cases to it. Are there any gotchas we should consider when continuing to adopt it within Android?
Yeah, so there are a lot of new features which are getting added to IOUing. For instance, the new IOUing op command, which is being used in the UBLK driver, which is really promising. So so some of the features we may have to see how exactly it fits to the Android ecosystem. For instance, let me give you an example. The SQ poll feature, which is really good because it cuts down the syscalls. But having said that, it constant polling it hogs one of the CPUs. Now, is it good for the Android ecosystem? Probably not, because one thread will be you're effectively taking out one CPUs, which constantly polls. So it's important to see the trade-offs and keep track of what are the new features which comes in.
Yeah, I think one of the gotchas I would warn people about is IOUing is under very active development. And
Yes,
so there are constantly new IOUing commands being added. And sometimes there are exciting high severity CVEs that come with some of them. And at the moment, we don't have good ways of controlling, new IOU ring commands via something like setcomp or SE Linux, as far as I know. And part of that is because IOU ring is intended to be really fast. And so that stuff will come over time, but it may be that some investment is needed before people try to use IOU ring outside of very restricted system contexts inside Android. At least that'd be my recommendation.
Yes, makes sense. So you're right. I do see some of the LSM SE Linux policies being added for IOU ring op command, which is a recent command which got added. But yes, it's important to understand that. I mean, for instance, in our use case, the daemon completely works under the root privileges, so we are completely in control of it. Yeah, as and when we go down the path with more SE comp and SE Linux capabilities added, then we can think of exploring IOU ring on the other set of use cases.
Yeah, so a security IOU ring CMD LSM hook was just added. Do you plan on using that?
We don't know, since we are still exploring the UBLK block driver. We haven't reached that far yet, but certainly yes. If the SE Linux capability has been enabled, then we will have to add it.
So yes, that's right, that SE Linux and SMAC both, there are hooks in both, and that's applicable for 5.19. It will be backported, and it is, I mean, originally it was done for 6.0.
Great. Okay, that's good to know. Yep.
All right. Thank you very much. Next speaker, Yanela, the floor is yours.
Hello. So my name is Ioana Voinescu. I am part of the Power Management Kernel team in ARM, and I'm going to talk to you today about the impact of recent CPU topology changes on Android phantom domains. This is something that myself and Dietmar have been discussing for a while with regards to the impact on the scheduler topology. These changes affect the ARCH topology driver, so they will be affecting ARM64 RISC-V, and they were developed in a large majority by Sudeep Hola, part of the kernel team. So here we're just discussing of the impact of those changes on Android. I'm going to quickly go through an introduction on topology, discuss these topology changes and a bit of phantom domains, and then we'll see how these changes impact phantom domains. The topology examples in this presentation are going to be referring to a Qualcomm platform, the RB5 platform. This is quite representative for a typical Android mobile platform. So it has 4 little CPUs, 3 medium CPUs, 1 big CPU, so three capacity groups. And it's what we call a dynamic system. That is a DSU. It has a single DSU cluster with shared between all of the CPUs, having an L3 cache and some coherency logic, Snoop filters, and so on. And it's important to make a differentiation between sort of a dynamic system, one of the single cluster DSU dynamic systems, and what we call typical big little systems, in which we had multiple clusters. So each of the capacity groups of CPUs, so little CPUs with the same microarchitecture, would have their own cluster with probably a shared L2 cache, and the same thing, cache coherency logic shared, and a separate cluster for big CPUs. So there's a bit of differentiation there in order to set a bit the scene regarding phantom domains. So in regards to topology, to set the scene about what is the information we are going to be using. So CPU topology information and sort of CPU adjacent information comes from device tree and from ACPI, and it's exposed via sysfs through to the user. So basically we'll have information on CPUs belonging to the same core, or CPUs belonging to the same cluster, the same package, and so on. And it's exposed through sysfs via the folder you see on the right-hand side. And the same thing, other information on topology exposed to the user is cache information. So we have cache types, and especially relevant here are going to be CPUs that are sharing a certain cache. Topology information coming from DT or ACPI is also used by the scheduler, and it's sort of being compiled in the form of information relevant for scheduling under this scheduler domain hierarchy. So the functions you see in sort of midsection of the slide are functions that determine the CPUs that go in each of these scheduler levels, and they are some of them are architecture specific, so these will be specific to the arch topology driver. For Android systems, for mobile systems, usually we are looking at MC, multi-core level, which contains CPUs sharing last level cache. The function that determines the CPU usually selects the smaller group between NUMA package and LLC, but this is typically last level. This is typically CPUs that are sharing last level cache, and then at die level we'll have CPUs across multiple packages. There is a newly introduced level, which is the CLS cluster level. I'm not going to discuss it here, although it has a bit of an impact, but it would be too long of a discussion. I'm happy to take questions later on this. So sort of going away from a bit of topology introduction, the recent changes done by Sudeep on this had as a motivation bringing these topologies closer to hardware, having better topologies that describe hardware better. And one of the things that was lacking was the fact that when going for, this is for DT systems, when going through the CPU map entry in DT, when CPUs were grouped in different clusters, the cluster index was used as a physical package ID, which meant that they were actually presented to user space and scheduler as belonging to different packages, which it was not actually accurate to the hardware of that platform. Under sort of the same topic, and actually that first point is the most relevant for phantom domains later, but under the same topic, basically that creates the discrepancy between topologies you would obtain with a DT description versus topologies you would obtain with an ACPI description for the same platform. So that was improved by these patches as well. Also, these patches improve the detection of shared caches, and especially important for the scheduler is the last level cache. So that uses the cache info hierarchy in order to obtain this information. It doesn't necessarily change anything for Android systems and these phantom domains. Going further to discuss phantom domains, basically phantom domains are device tree clusters that are grouping together CPUs of the same microarchitecture. So this is not necessary. So they come sort of from a bit of the history of the energy model and ES. So the old style energy model and ES were initially demonstrated on Android systems. And at that point, the energy model information was attached to the scheduler domain hierarchy to shed groups. And for this reason, when there was sort of a when this old style energy model was used together with dynamic systems, there was a need to use these phantom domains in order to mimic those typical big little systems. So CPUs, as you see on the left-hand side, CPUs were grouped together under these clusters, despite them actually all of them sharing a last level L3 cache and sharing the same logic, so not actually being separated in hardware in these clusters, but it was needed by software. After moving to a simplified energy model and with the added support upstream for dynamic system, these phantom domains are no longer needed, but they are used on today's Android systems. So sort of finalizing with two slides here on the impact on of these changes on phantom domains. So an arching conclusion here is the fact that these phantom domains will no longer be recognized as previously by the new CPU topology parsing code. That is, they will be handled as if they were not present. So if previously, as you see on the left-hand side, for a system, an RB5 system with phantom domains before these patches in mainline, you had little CPUs grouped together in a separate package, and then medium CPUs separated in a package as well, and so on. This will be, let's say, sort of made invisible by the new patches, which properly now handle those CPU map clusters as clusters and sockets as sockets and so on. So they describe a more accurately hardware, and you would obtain a topology that actually reflects hardware. That is a topology in which all CPUs are sharing an L3 and they share the same package. So one important information for user space regarding the users of phantom domains is that information on these groups of CPUs sharing microarchitecture and sharing CPU capacity, if package CPUs or package CPU list or CPU siblings list was used before to determine which groups of CPUs were sharing capacity, were sharing microarchitecture, now is no longer possible. Is there any question? Oh, I think it's just a bit an echo. In regards, under the same lines, the impact of the scheduler is quite similar. That is, previously with phantom domains, before these patches, we would have two levels in the scheduler domain hierarchy. So under MC, there will be CPUs grouped together, CPUs that were sharing capacity and microarchitecture. While at die level, we will have all of the CPUs across all of these packages. After these patches and a proper interpretation of hardware, there will be a flattened topology, and all CPUs will belong to a single level MC, as they should, as they are sharing a last level cache and L3 cache. The impact on the scheduler, so going from phantom domains, going from these two levels in topology to a single level in topology, the impact is so we wouldn't see any impact in energy aware scheduling. The new ES and the simplified energy model in the scheduler doesn't actually attach itself to the scheduler domain hierarchy anymore. It has its own data structure, so there's no impact there. While the way that a CPU is being selected for task placement by ES, it actually goes through the CPUs in a domain that spans all CPUs that spans all capacities in a system. So it doesn't really matter if those CPUs are at die level or at MC level. Some impact could happen in the load balancer. So as you know, load balance is done more often at lower level in the hierarchy rather than at higher levels. So all CPUs will be involved, or there will be load balancing happening between all CPUs more often. And probably the structure of shared groups will also create some differentiation between these two systems. But the most important impact possibly is the fact that if there is any functionality behind vendor hooks that are relying on these phantom domains, so if there's any functionality, any additions to the scheduler that are relying on groups of CPUs sharing microarchitecture and capacity at MC level, those will no longer work as expected. So as a conclusion for everything, so this was just to more or less raise awareness for of these changes, and to discuss if there is a need for phantom domains, and if there is a need, it would be good to try to find other solutions rather than, let's say, these DT changes, these DT phantom domains that will not work as expected when these new topology changes are adopted in Android systems. That is all from me. If anyone has any questions.
Yeah, hey, Saravana here. I have a question.
Yeah, yeah.
Doesn't this break backward compatibility with older DTs? Like, that's something we try not to do. So why are we just going and breaking it?
So it doesn't break backwards compatibility with older DTs because it's just fixing in CPU topology parsing code the interpretation of clusters. Well, it's not necessarily the interpretation of clusters. Now in CPU map in DT, you can have clusters, groups of CPUs belonging to the same clusters, and you can have sockets, groups of CPUs belonging to the same socket. Previously, so that was a problem for Arch topology parsing code. Those clusters were interpreted as sockets, so that was a bug that resulted in a different scheduler topology, which didn't actually, for typical big. LITTLE systems, didn't have a visible impact. But for dynamic systems, if the use of clusters in DT is abused, which phantom domains would be, that would actually result in a potentially broken topology. I hope I've answered your question, right?
I am not, but I have a second question. Maybe that'll clarify it. Sorry, I missed the really initial part of this talk, but why are we removing phantom domains, or what you call as phantom domains?
So
Changing how those things used to work. Now you're spreading the task across all microarchitectures when we didn't do it before. So what is the pressing need to do it now?
So we're not necessarily removing phantom domains. So phantom domains was just a sort of configuration added to DT in order to support, let's say, early systems that were using EAS, the old style with the old style energy model, while dynamic was present. From the scheduler point of view, actually the new topology without phantom domain, so let's say phantom domain is just an abuse of DT, of clustering in DT, which is not reflective of hardware. So with dynamic system, actually all CPUs are equal. They're all sharing the same DSU logic. So migrations of tasks between CPUs would happen in the same amount of time between all CPUs. So that is a more accurate description of hardware. It's not something we're removing. It's something that gets updated to match the most recent hardware. Oh, sorry about that.
Yeah, you're gonna have to take that offline. I'm gonna invite the next speaker over, Lucas, if you wanna join in.
Thank you very much.
Thank you. Thank you, Anil. So, Lucas, if you're online, if you want to put your webcam on and the mic on.
Yes, I'm online. Hi, guys. Can you hear me?
Yep. Go ahead.
Thanks. My name is Lukasz Luba. I work for ARM in the Kernel Power team. I'm going to show you some work regarding the energy model and our plans for this. So here is the agenda. We have energy model and EAS for quite a while, but we have some issues, mostly because of the recent changes for the topology in SoCs. So we get a real tri-gear systems where we have a real big core and then some mid cores and little cores. And those, they are behaving differently with the old models that we have. So this is improvement to tackle this issue. So what we have now, the current energy model is a constant array which holds the frequency, power, and cost for the EAS. And those values are used for the decision for the EAS to place the task in the most optimal way. And there is one energy model for each performance domain. And the performance domain is, for instance, a little cluster or a mid cluster or a big cluster. We have some pre-computed cost in there to speed up some EAS calculation. And we've done some improvements recently, step by step, like increasing the resolution in the cost field, then increasing the resolution from milliwatts to microwatts in the power field, and recently removing some margin in the EAS when we compare the task placement and we consider the prev CPU and the next CPU, and there was a 6% margin. So we removed that as well. And why? Because the real tri-gears, they have really close power performance curves that I will show you in some next slides. So we are trying to make the model better reflecting that overlapping area between those two cores, the big and the mid. And here is how EAS uses the energy model. So when the task wake ups, we try to evaluate from each performance domain less loaded CPU, less utilized CPU, and we use the energy model to get the clue how much it would cost to put the task in such a performance domain. But this is not ideal world because the real hardware actually is more dynamic, and the energy, the power of the CPU can change. And one of the reasons that it can change is because of the temperature of the whole SoC. And here is the explanation between the power and temperature. So the total power that we can measure on the CPU using some energy counters, for instance, it's actually there is a split between dynamic power and static power. That static power is not that big with the newest technology, but it can vary between the cores. And the big cores, the more performance cores, they are built with different goals. To not power efficient, but to have a higher frequency and better performance. So they leak more. And here is also the relation between the increase of temperature by 20 degrees, then we actually increase by 2 times that leakage contribution. And if we know that, we actually can derive the new power performance curve for that core. And this is the relation when the big core actually runs at normal temperature, or if it runs at some hot temperature, because there is a heat generated by the GPU, and the CPU has increased the temperature by 20 or 30 degrees more than normal. So normal, I mean running some benchmark that we derived the energy model based on the tests and experiments. So if the curve shifts goes up, then we actually can leverage that because we have another CPU in that SoC, which is the mid core. And here is actually a chunk of those two curves when they actually overlap, the mid core and the big core. And also there are those curves actually with increased temperature. So when the mid core is hot as well. And as you can see, the mid core, the green line, the green curve is not that affected like the big one. So there is a potential area where we actually can put a task in different way if we know this. And here is some experimental results that I've made, and it shows that in some recent phone, when the GPU actually is loaded around 1 watt or 1.5 watts, we increase the CPU temperature by around 20 degrees versus the normal temperature of that CPU running that workload. And it affects the power usage of the big by plus 15 to 18.5% versus the mid core actually running the same workload. It's affected less, 5 to 8%. So then there is a need to adjust the energy model in runtime if you play a game, for instance, to reflect that the actual power performance curve of the big core goes up. And then you might consider in a task placement the mid core instead of the big core. And here is how we do this. I have implemented this last year, and it can be seen on Gerrit. EAS has some requirements, and it uses the data in RCU fashion. So I have just used another RCU pointer in there to swap actually the energy models. And there is some also requirement to not expose this interface to user space or to not affect some other frameworks like thermal, but only influence the scheduler, the EAS. And that's why we have this RCU mechanism, and we can change actually the values in runtime from, for instance, a kernel module, a vendor module, which is aware of these changes of the temperature and the conditions of the chip. And then EAS will just benefit from the new power field and the new cost field values to evaluate during the task placement. So that should be quite safe mechanism from the scheduler point of view, but there are some drawbacks. So we actually manage the memory inside the framework, so you cannot just plug in the module and memory, and because that might disappear. So we actually own the memory inside the framework, and we populate for every frequency we populate the values, and we use that callback to get the new power value for each frequency. It takes around 10 microseconds at the big core running at 1 gigahertz to update that value, actually the whole array. But it's a quite safe mechanism, and actually there is no limits like for double buffer and some concurrent writers, etc. And there are some other requirements for this actually feature, because it opens some new possibilities, not only to adjust the energy model due to temperature change, but also because it can be changed after the boot is finished. You can plug in a new model because you have some limitation in normal code in the OPP framework and DT to calculate the energy model. You can just easily exchange those values. The second point is there is some chip lottery. So if you're lucky, you get some nice chip which leaks less, but the same phone can be actually affected by some binning. So the chip can leak a bit more. But the module can be loaded, and actually EAS might be aware of that those new values for this phone are present. So that's the second. And the third one, actually, we can also use this interface to optimize some workloads and to influence EAS via energy model for better utilizing the hardware resources during, for instance, a game or video recording or web browsing, because that's also possible. That's all that I have. There is a plan to send RFC to the list soon, so we could discuss there if you have some requirements regarding this API, we can discuss there. There is no plan to... Oh, sorry, go ahead.
Is there a quick comment on the last point, if you go back one slide?
Yes.
Where using the energy model for different use cases, This just feels like an abuse of trying to place tasks by faking values for the energy model to kind of push threads one way or another instead of actually being a real energy model. It becomes another policy tuning thing. And I've seen
Well,
some
mhm.
people kind of abuse it that way. So that's the one thing I don't like about this. Everything else seems pretty good.
Well, we cannot prevent that. If you open that API, it can be just used. But another question is, what is the real power value that has to be stored in there? While the CPU can drain different power, it depends on the workload that it is running. So if you have some heavy asymmetric floating point computation, it's totally different than, for instance, some lightweight text or some text compression.
Capture, right? And then we should take that into account.
Yeah, so
Case where they're kind of guessing. Dietmar wants to say something.
That's exactly what we want to talk about tomorrow when it comes to the problems we have with the energy model. But you can see what Lukas said here. We can change the EM runtime. We can change the energy model at runtime already with this patch. But what we really want to do is to constantly change the input for the energy model. So you have one energy model, but all the input you were just saying should essentially influence the energy model dynamically during runtime. Exactly. Instruction is one thing, yes, but you can see this as like a cheap implementation, but the real thing will take much more time and thinking to get it right.
yes. So
Just energy model discussion
Yeah, of
tomorrow
course, I'll
afternoon,
come,
and then we can see.
So this started as an improvement, like a step by step. As I said at the beginning, we first increased the resolution inside the cost field, then inside the power field. Then we removed the margin, the 6% margin. All this is around the constant EM. Now we try to reflect better the reality of the leakage, which has some impact, especially for this mid versus big cores. But the big goal for us would be, like Dietmar said, it would be discussion tomorrow, because the energy model is actually one-dimensional. It doesn't reflect the reality. So the issue, we know the issues, but we cannot tackle them at once.
This is my one point is like completely agree with what you're trying to do. Makes complete sense. Just the interface we're giving is the part where I'm like, maybe there's a better way to do it where it can't be abused. That's all.
Yeah, but so there's a third point here on that slide. We actually, if we open that floodgate, we cannot prevent this, right? If they would like.
I have some thoughts on it, but
Sorry to cut
Okay.
you guys off, but slowly the official time is over, and even though you're last
Okay.
speaker, I respect the time that we had
Yeah,
allotted.
man.
So thank you
Sure.
very much.
Thank you.
And thank you all for having attended. There is a BOF tomorrow, so don't forget that. Remind me, John, the time again is? Sorry, bad memory here. Is it noon, I think? So, okay, so there's a BOF tomorrow at noon. So if there are any topics that you want to discuss, like for example, this one, that need to be picked up tomorrow, there will be ample time for that. All right, thank you again all for attending, and enjoy the rest of the conference.
Thank you.